For a long time, the Andromeda galaxy has been seen as nothing more than a faint blurry patch in the night sky. Some believed it was just a nebula, a small cloud of gas inside our own Milky Way, but others wondered if it might be something much bigger, maybe even a whole galaxy by itself. When we finally discovered the truth, it completely changed how we saw the universe. Andromeda is not just another bright object in the sky. It is the biggest galaxy in our local group, holding about 1 trillion stars and many mysteries we still haven't solved. Over billions of years, the Milky Way and Andromeda are slowly moving toward each other, and one day, they will come together to form a brand new galaxy. What secrets might this huge neighbour be hiding? Could it have planets we haven't found yet? And could humans ever travel far enough into space to reach it one day? Before we embark on this journey, drop a comment below and tell us where in the world you're watching from. Then, settle in as we take you on a journey to the centre of the Andromeda galaxy. At the start of the 20th century, a deep mystery stayed in the minds of astronomers, a puzzle so serious that solving it would forever change humanity's understanding of the universe. Among the countless stars that shined in the night sky, a faint, blurry patch of light caught the attention of scientists. This object was known as the Andromeda Nebula. At the time, it was just one among many such smudges in the skies, often called nebulae, a word that suggested clouds of gas floating within our own Milky Way. The main question, however, was nothing less than shocking. Was Andromeda only a cloud of gas within our galaxy? Or was it something far more surprising? An entirely separate galaxy? A distant island universe on its own? The common view in the early 1900s was that the universe was far smaller than we now understand it to be. The Milky Way, the wide band of stars that stretched across the sky, was thought to contain all that existed. Every star, every planet, every bit of dust and gas. In this picture, the Milky Way was everything. Any faint glow beyond it was usually assumed to be nothing more than a local cloud of gas, slowly gathering into new stars. Andromeda, with its soft, spread-out light and smooth spiral shape, was listed as one of these nebulae. Its beauty and shape, however, sparked curiosity and debate. By the early 1900s, astronomers began to question the true nature of Andromeda. Some brave scientists suggested that this faint light might not be part of the Milky Way at all. Maybe, they said, it was a huge collection of stars, a separate galaxy like our own, moving quietly through the darkness of space. This idea was nothing short of shocking. If true, it showed that the universe was hugely larger than anyone had dared to imagine. The Milky Way, huge though it was, would no longer be the only star system in existence. Instead, it would be just one among countless galaxies spread throughout the universe, each containing billions of stars, possibly with their own planets and their own mysteries. One of the main arguments against the idea of Andromeda as a separate galaxy came from the respected astronomer Harlow Shapley. In 1917, Shapley carried out a detailed study of the Milky Way and guessed its size to be about 300,000 light-years across. This was an amazing number by the standards of the time, almost beyond understanding. Shapley and others who agreed with him believed that the Milky Way was so large that there could be no need for other galaxies. All the so-called nebulae, they argued, were probably part of our own galaxy, just clouds of gas or groups of stars forming within it. The idea that Andromeda could lie outside the Milky Way, separated by millions of light-years, seemed impossible, almost silly. The huge size needed to allow another galaxy was hard for anyone to imagine. Yet not everyone agreed with Shapley. A dedicated astronomer named Heber Curtis offered a very different view. Curtis looked at the evidence in a new way and suggested that Andromeda and several other spiral nebulae might indeed exist far beyond the edges of the Milky Way. He pointed to an especially interesting clue, the observation of novas, or exploding stars in Andromeda. Novas briefly brighten, becoming extremely bright before fading back into darkness. Curtis noticed that these novas appeared much dimmer than those seen within our galaxy. If these were similar events, their faintness could only be explained if Andromeda was located at a huge distance, far beyond the limits of the Milky Way. Curtis also studied the shape of Andromeda itself. Unlike a simple gas cloud, Andromeda showed a clear spiral shape, a smooth swirl of light that looked like the shape of our own Milky Way. While some nebulae within the Milky Way seemed messy or spread out, these spiral forms had a clear, organised pattern. If they were only gas clouds, it was hard to understand why they would take on such ordered shapes. But if they were separate galaxies, huge collections of stars each held together by gravity, then their spiral shapes made perfect sense. Here was an exciting possibility. The night sky might be filled with countless galaxies, each a huge island of stars like Andromeda itself. This argument between Shapley and Curtis reached its dramatic peak in 1920 during what would come to be known as the Great Debate, held at the Smithsonian Institution in Washington, D.C. It was a historic event, bringing two of the era's greatest thinkers together to argue in public about the true shape of the universe. Shapley, speaking for the one galaxy view, argued strongly that the Milky Way's enormous size made the idea of other galaxies unnecessary. Curtis, on the other hand, supported the idea of a universe full of galaxies, saying that Andromeda and other spiral nebulae were separate star systems, not part of our own. The debate was lively, energetic, and filled with complex arguments about observations, distances, and the limits of knowledge at the time. Yet, in the end, no clear winner appeared. Both men gave strong points, and the evidence available then could not settle the question. The true nature of Andromeda stayed one of astronomy's greatest mysteries. Even though the Great Debate had no clear answer, the search for the truth continued. Astronomers kept studying Andromeda, looking for a way to measure its distance accurately. It was in 1924 that a breakthrough happened, thanks to the hard work of Edwin Hubble at the Mount Wilson Observatory in California. Using the powerful 100-inch telescope, a wonder of engineering at the time, Hubble began a careful study of Andromeda, looking for clear proof of its true identity. His work would forever change the field of astronomy. Hubble's main tool was a special type of star known as a Cepheid variable. These stars are amazing because they brighten and dim with a regular pattern, changing over a predictable cycle. Earlier in the century, the astronomer Henrietta Swan Leavitt had made detailed studies of Cepheid variables in the Small Magellanic Cloud, a nearby galaxy. She discovered an important relationship. The longer a Cepheid cycle, the brighter it really is. This meant that by observing how fast a Cepheid changed in brightness, astronomers could find out its true brightness. Comparing this real brightness with how bright the star looked from Earth allowed them to calculate its distance. It was a method both simple and accurate, giving a direct way to measure the huge distances of space. Hubble used this method on Andromeda and found several Cepheid variables within the nebula. Calculating their distances, he reached a shocking result. Andromeda was more than 2 million light-years from Earth. This measurement was beyond any doubt and placed Andromeda far outside the Milky Way. For the first time, astronomers had solid proof that Andromeda was not a gas cloud within our galaxy, but a separate galaxy entirely, an island universe on its own. Hubble's discovery broke the long-held idea of a single galaxy universe. Suddenly the universe grew in the minds of humanity. The Milky Way, once imagined as the entire universe, was now shown to be just one galaxy among countless others, each containing billions of stars, possibly with their own planets, dust clouds, and cosmic events. The effects of Hubble's work were deep and immediate. The idea of an island universe was no longer a guess, it was a proven fact. The universe was unbelievably huge, filled with galaxies spread across distances that pushed the limits of human understanding. As telescopes became even more powerful, astronomers began finding more and more galaxies, some larger than the Milky Way, others smaller and more distant, spread across the emptiness in amazing numbers. The simple night sky that had once looked familiar and limited now appeared as a huge sea of galaxies, each a cosmic city of stars spinning and shining across unimaginable distances. Hubble's discovery also opened the door for a new time in cosmology, the scientific study of the universe as a whole. No longer could astronomers limit their studies to the Milky Way. The universe itself became the laboratory, and questions about its size, shape, and beginning came to the front. The idea of a still, limited universe changed into the understanding that the cosmos is huge, active, and full of mysteries waiting to be studied. Observations of galaxies led to more discoveries, including the fact that the universe is expanding, an idea first suggested by Hubble's later work in the 1920s and 1930s. The change in astronomical knowledge in the early 20th century is a strong reminder of how humanity's understanding of the universe can grow. What was once believed to be everything, the Milky Way, was shown to be only one part of a far larger and more complex reality. Andromeda, once only a faint, mysterious patch of light, became a symbol of curiosity, hard work, and the human desire to explore the unknown. The debate between Shapley and Curtis, the careful measurements of Hubble, and the insights of Henrietta Swan-Leavitt together show the team effort and step-by-step nature of scientific discovery. Each astronomer, with careful observation and brave ideas, helped create an understanding that changed our view of the universe forever. Looking back, the story of Andromeda reflects the larger journey of science itself. First observations lead to guesses, which then face debate and questioning. Only through exact measurement, careful thinking, and new methods does certainty appear. Andromeda's discovery as a galaxy beyond the Milky Way was not just about one object. It was a doorway to a new view of the universe, a change in how we see our place in it. The night sky, once believed to be small and understandable, became a huge and endless frontier, each new discovery inviting deeper questions about the origins, growth, and final fate of the universe. By the mid-20th century, astronomers had listed thousands of galaxies, each different in shape, size, and structure. Some were grand spirals spinning like Andromeda itself. Others were elliptical, large and round, while still others were irregular, without any clear shape. The variety of galaxies further showed the richness and complexity of the universe. Human beings, for the first time, could truly understand not only the hugeness of space, but also the amazing variety of the objects within it. The idea that our galaxy was everything had been replaced by the understanding that it was only one of an enormous number, each a world of stars and possible planets. This larger view of the universe also inspired deeper thinking in philosophy and culture. If the Milky Way was not alone, then humanity's place in the universe might be more modest than previously believed. Yet, at the same time, the discovery of countless galaxies suggested possibilities beyond imagination, worlds and civilizations that might exist somewhere else, separated by millions or billions of light years. The night sky became not just a background for human observation, but a huge picture of cosmic structure, each galaxy a thread in a universe that was far larger, older, and more complex than anyone had ever dared to dream. Even after the important discoveries of Edwin Hubble in the early 1920s had changed the field of astronomy, many doubts and unanswered questions continued to remain among scientists. Hubble's work had greatly changed the way humans understood the universe, showing that the faint, smudgy object in the night sky known as the Andromeda Nebula was not a simple cloud of gas within the Milky Way, but a separate, huge galaxy in its own right, located far beyond the limits of our own star system. This discovery alone was enough to shake the foundations of astronomical thought at the time. Yet, as is often the case in science, progress did not follow a straight or simple path. Confirming that Andromeda was indeed a galaxy did not suddenly solve all uncertainties about the universe. Instead, it opened the door to a whole new set of mysteries and challenges, many of which confused astronomers for decades. One of the first and most urgent questions concerned the brightness of galaxies. If these vast groups of stars were actually millions of light years away from Earth, as Hubble's measurements showed, then their true brightness, the amount of light they produced, must be far greater than anyone had previously imagined. For many scientists, this was a difficult idea to accept. The thought that a single galaxy, made of billions of stars, could give off such huge amounts of light across such hard-to-imagine distances seemed almost impossible. It was not just a matter of size, but also a matter of understanding the processes that powered stars themselves. At that time, astronomers had only a basic grasp of the inner workings of stars, and the main theories of stellar energy were still the subject of lively debate. In the early decades of the 20th century, the main explanation for how stars produced energy involved gravitational contraction. According to this theory, stars shone because their huge mass slowly pressed inward under its own weight, making heat and light in the process. This idea could explain why stars gave off energy for a time, but it had a serious flaw. It could not explain the incredibly long lifespans of stars. If stars were powered only by gravitational contraction, they would burn out in tens of millions of years, far shorter than the billions of years shown by observations of the universe. This problem became especially serious when applied to galaxies. Hubble's work showed that galaxies contained billions of stars, each shining brightly. If this was true, then the known ways stars produced energy could not possibly explain the observed brightness of galaxies as a whole. Scientists needed a new understanding of the processes happening within stars to match these observations. It was not until the mid-20th century that this problem was solved, when researchers finally confirmed that stars got their energy from nuclear fusion. In this process, hydrogen atoms deep within a star's core fuse together to form helium, releasing huge amounts of energy in the form of light and heat. This process explained both the enormous brightness of individual stars and their ability to shine steadily for billions of years. With nuclear fusion as the energy source of stars, astronomers could finally begin to understand how entire galaxies, made of countless stars, could produce the amazing amounts of light that Hubble had measured. Yet, brightness was only one of many questions that remained. Another puzzling issue involved the spread of galaxies across the universe. If the cosmos was indeed filled with countless galaxies, why did they seem to be unevenly spread across the sky? Early surveys of the heavens showed that galaxies were not randomly scattered. Instead, they tended to gather in certain areas, leaving other areas fairly empty. Some astronomers wondered if this gathering was simply an illusion caused by the limits of the telescopes available at the time. Others suspected that these patterns were real, and that galaxies were naturally arranged in groups and clusters. If this was the case, a new question arose. What force was responsible for creating these structures? Gravity seemed like the obvious answer, but astronomers in the early 20th century lacked the tools and exact measurements needed to fully study the motions of galaxies on such a huge scale. The motions of these cosmic groups remained mostly mysterious. Making things more difficult were early attempts to measure the motions of galaxies. Hubble had shown that in general galaxies appeared to be moving away from Earth, a discovery that became the foundation for the idea of an expanding universe. However, exceptions to this pattern puzzled astronomers. Some galaxies showed very little redshift, suggesting that they were not moving away as quickly as others. Even more strangely, Andromeda itself seemed to be moving toward the Milky Way, rather than moving away. How could this be explained with the expanding universe model? It would later be understood that the overall expansion of space did not stop galaxies from moving independently under the pull of their mutual gravity. In the case of Andromeda and the Milky Way, their closeness was enough that the gravitational pull between them beat the general expansion of the cosmos, setting them on a slow collision course that would continue for billions of years. While Hubble had confirmed the huge distance of Andromeda, the status of the many other spiral-shaped objects listed in the night sky remained uncertain. Were they all equally distant galaxies, or were some much closer, perhaps even part of our own Milky Way? Figuring out the true nature of these objects required careful observation and study. In some cases, objects that looked like spiral nebulae were later found to be completely different things, such as planetary nebulae or the remains of supernovae within our galaxy. The line between galaxies and other sky objects was often hard to see, showing the challenges astronomers faced as they tried to classify the huge and varied contents of the universe. The discovery that galaxies were enormous groups of stars also raised basic questions about star formation itself. How did stars form within these galaxies, and did all galaxies produce stars at the same rate? Early observations suggested that some galaxies were far more active than others. Certain galaxies contained areas that glowed brightly, showing strong star formation, while others seemed calmer, with less obvious star activity. The reasons behind these differences were not immediately clear, and astronomers needed more data to understand the processes driving star formation across different galaxy environments. Beyond the workings of star formation, scientists also struggled with questions about the change of galaxies over time. Had galaxies always existed in their current shapes, or did they change and grow over billions of years? The challenge in answering this question came from the nature of light itself. Light from distant galaxies takes millions, sometimes billions of years to reach Earth, meaning that observing faraway galaxies allowed astronomers to see them as they were long ago, not as they are now. However, the telescopes of the early 20th century were not yet strong enough to observe the most distant galaxies, stopping scientists from studying the earlier stages of galaxy formation. As a result, astronomers could only study the galaxies within reach of their instruments and make educated guesses about the past. Even with these uncertainties, the idea that Andromeda was a galaxy slowly became widely accepted within the scientific community. The evidence in favour of this conclusion was simply too strong to ignore. The careful measurements of distance, the observed structure of the nebula, and the comparison with the known properties of star systems all pointed to the same conclusion. Andromeda was not a small feature within the Milky Way, but a huge separate galaxy, similar in size and complexity to our own. Yet, as is often the case in science, each new answer seemed to raise more questions than it solved. The confirmation of Andromeda's galaxy status marked the beginning, not the end, of the study of galaxies. As astronomers continued their work, the mysteries of the universe grew even more. How exactly were galaxies spread on the larger scales? What determined the shape and structure of a galaxy? Why did some galaxies appear to form stars quickly, while others seemed almost inactive? And what would the study of even more distant galaxies show about the history and change of the cosmos itself? Each of these questions required not only careful observation, but also a deep theoretical understanding, and scientists were only beginning to develop the tools needed to explore them. The arrival of more advanced telescopes, the development of spectroscopy, and the improvement of mathematical models of gravity and motion would slowly provide the answers, but the path forward was far from simple. In addition, the study of galaxies forced astronomers to rethink their understanding of time and size. The universe was far larger than previously imagined, filled with countless star systems, each containing billions of stars, many with their own planets and possibly other structures. Human ideas of space, distance, and time had to grow to fit this huge cosmic arena. Distances that had once seemed impossible to understand now became measurable in millions or billions of light years, and the very idea of the size of the universe had to be reconsidered. The faint glimmers of distant galaxies were not just points of light in the sky. They were windows into the past, views of objects as they existed millions or billions of years ago, long before the Earth itself had formed. Even today, the questions that began with Hubble's discoveries continue to inspire astronomers. Modern research into galaxy formation, dark matter, dark energy, and the large-scale structure of the universe builds directly on the foundations laid by Hubble's observations. While the tools and techniques available to astronomers have advanced greatly since the early 20th century, the spirit of curiosity, the drive to question assumptions, and the willingness to face uncertainty remain at the heart of the field. Hubble's confirmation of Andromeda as a galaxy was not the end of a story, but the beginning of an ongoing exploration that continues to unfold, showing a universe more huge, complex, and amazing than anyone could have imagined a century ago. In the end, the study of galaxies shows the true nature of scientific inquiry. Answers lead to new questions. Each discovery lights up certain parts of the cosmos while hiding others, pushing further investigation and deeper thought. The realization that Andromeda was a galaxy did not close the book on astronomy. It opened a whole new volume, one filled with mysteries that challenged human understanding and stretched the imagination. The journey from seeing Andromeda as a faint smudge in the night sky to recognizing it as a wide-spreading galaxy millions of light years away was not just a success of observation, but a sign of the persistence, creativity, and courage of scientists willing to rethink the universe and their place within it. Through the decades that followed Hubble's early work, astronomers slowly began to understand the complexities of galaxies. They learned to measure distances with growing accuracy, track the motions of stars within galaxies, and understand the processes that control the birth and death of stars. They discovered that galaxies could collide, merge, and change over billions of years, forming structures of incredible variety and beauty. They realized that galaxies were not isolated objects, but were part of a vast cosmic web, influenced by gravity, dark matter, and the mysterious expansion of space itself. And yet, despite all of these advances, the universe kept its ability to surprise, to challenge assumptions, and to inspire wonder. For countless centuries, the faint patch of light that we now know as the Andromeda Galaxy puzzled stargazers. To the naked eye, it looked no more than a small smudge against the black background of the night sky. Some thought it was simply a hazy cloud of gas inside our own Milky Way. Others dared to imagine that it might be something much larger, perhaps a great island of stars far beyond our space neighbourhood. With the progress of telescopes and the hard work of astronomers, the truth was finally shown. That hazy blur was not a nearby cloud, but an entire galaxy of its own, a huge star system stretching for hundreds of thousands of light years. Today, this galaxy is known by several names: the Andromeda Galaxy, Messier 31, or simply M31. Whatever name is used, it has become one of the most studied and praised galaxies in the entire universe. Once astronomers moved past the great argument of whether Andromeda was a galaxy at all, their attention turned to its inner workings. They wanted to know what it was made of, how it was shaped, and what secrets were hidden in its huge size. What they found was not a simple system of stars, but a grand space city filled with billions upon billions of suns, drifting rivers of gas, strange halos of unseen matter, and marks left behind by violent crashes with other galaxies. The deeper they looked, the more they saw that Andromeda was not a still object but a living, changing system shaped by space forces across billions of years. Much like our own Milky Way, Andromeda is home to stars of every age and kind. Some are fiery blue giants that live short, bright lives before exploding into supernova. Others are tiny red dwarfs, dim and long-lasting, which have burned quietly for more than 10 billion years. This mix of the young and the old gives the galaxy a nature that is at once active and aged by time. In its bright central bulge, the crowded heart of the galaxy, old red stars rule. Their warm glow is the light of suns that formed in the early days of Andromeda's life, when gas was plentiful and star-making was intense. These stars long ago used up much of the surrounding fuel, leaving behind a group that is older, steadier, and redder in colour. Yet beyond this old core, the story changes. Stretching outward in wide spiral arms are great clouds of gas and dust, thick enough to block starlight and heavy enough to fall in on themselves. In these arms, young stars are still being born. Some areas shine with the blue light of massive newly formed suns, each of them so hot and bright that their light outshines entire groups of older stars. To astronomers, these glowing blue areas are signs of ongoing creation. They show that Andromeda is not a galaxy that has finished its story, but one that continues to write new chapters in the language of stars. A galaxy made only of old stars would be a silent museum of space history, no longer making new suns. A galaxy filled only with young stars would be something just beginning its journey, still in the early days of growth. But Andromeda is neither of these extremes. Instead, it is a mix of the old and the new, a space balance that shows its long and varied past. Over billions of years, it has passed through cycles, sometimes bursting with star-making when gas is stirred or squeezed, other times falling into quieter periods when little new light is born. These cycles depend on the movement of gas, the needed ingredient of stars, which drifts and flows across the galaxy like a restless ocean. The supply of this gas is the key to Andromeda's ongoing growth. Most of it is hydrogen, the simplest and most common element in the universe. Huge clouds of hydrogen float in the spaces between the stars, sometimes thin and ghostly, sometimes gathering into thick knots of matter. When gravity pulls enough gas into one place, the pressure and heat rise to amazing levels. At a certain point, nuclear fusion begins, and a new star is born. This process is nature's greatest change, the turning of simple hydrogen gas into blazing starlight. Often, not just one star, but entire groups light up from a single massive gas cloud, lighting up the spiral arms like fireworks across the dark sky. Not all of the gas within Andromeda moves in neat order. Some streams of gas do not match the galaxy's overall rotation. These strange motions show that Andromeda has not always lived alone. Over its long history, it has swallowed smaller galaxies, pulling them apart with its strong gravity. When a tiny companion galaxy drifts too close, Andromeda grabs it, pulling away its stars and gas and adding them to its own shape. These space meals leave behind traces, faint rivers of stars stretched across the sky, twisted trails of gas, and broken patterns in the spiral arms. By studying these leftovers, astronomers can rebuild Andromeda's violent past, a history of crashes and mergers that shaped it into what we see today. Yet Andromeda holds more than stars and gas. Surrounding the entire galaxy is something invisible but massive, a huge halo of dark matter. This strange substance does not shine, reflect, or block light. No telescope can capture a picture of it, yet its presence is clear. It shows itself through gravity. In the early 20th century, astronomers studying galaxies noticed something puzzling. By all normal thinking, stars at the far edges of a galaxy should move more slowly than those near the centre, much as in our solar system, where faraway planets like Neptune drift slowly while the inner worlds race quickly around the Sun. But in Andromeda, and in many other galaxies, the stars at the edges were moving just as fast as those close to the core. There was only one answer. Some hidden mass must be giving the extra pull of gravity, holding the outer stars in place. The visible stars and gas were simply not enough to explain this effect, and so astronomers suggested the existence of dark matter, an invisible frame of mass surrounding galaxies. By carefully measuring the movement of stars and gas in Andromeda, scientists saw that most of its mass is not in the shining stars or glowing gas, but in this unseen part. The normal matter, the kind that makes up suns, planets, and people, forms only a small part of Andromeda's total. The rest is locked in dark matter, stretching outward in a huge halo that reaches far beyond the galaxy's visible disk. Dark matter remains one of the most deep mysteries of modern science. Decades of research have not shown its true identity. Is it made of some unknown particle, heavier than anything we can detect in our labs? Is it a sign of hidden laws of gravity that we do not yet understand? Whatever the answer, it is clear that dark matter plays a key role in shaping galaxies. Without its invisible gravity, the stars of Andromeda would drift apart like sparks in the wind. With it, they're held together, forming a wonderful spiral that has lasted for billions of years. Andromeda is not just a group of stars and gas, it is a space city with a complicated shape and a long dramatic history. When astronomers look at it, they do not see a single simple form, but instead a layered and living system that stretches across unbelievable distances and holds countless secrets about how galaxies are born, grow, and change with time. At the very heart of Andromeda lies a bright central bulge. This bulge is like the downtown area of a city, filled with stars packed together far more tightly than in the quieter outer areas of the galaxy. Most of these central stars are old, survivors from the early days of Andromeda when the galaxy was still young and full of activity. Their light blends together into a bright glow, which can be seen even from Earth through a telescope. Hidden within this bulge is the most powerful object of all, Andromeda's central black hole. This is no ordinary black hole, it is what astronomers call a supermassive black hole, a giant weighing millions of times more than our own Sun. Its gravity is so strong that nothing, not even light, can escape once it falls too close. Yet Andromeda's black hole is a strangely quiet giant. Unlike the central black holes of some other galaxies, which swallow huge amounts of gas and dust and blast out fierce jets of energy, Andromeda's central black hole takes in only small amounts of matter. Because of this, it does not shine with strong radiation or produce violent bursts of energy. Instead, it sits in relative calm, its great power mostly hidden, though its pull on nearby stars is huge. Moving outward from this dense core, the galaxy spreads into a thick disk filled with stars. This disk is not smooth or even, but is shaped into wide spiral arms that twist slowly outward. To the human eye, these arms would look like bright, glowing rivers of light curving through the galaxy. But these arms are not solid paths made of stars. Instead, they are more like travelling waves, patterns of density that move through the disk. As these waves pass through areas of gas and dust, they squeeze the material together, causing new bursts of star-making. This is why the spiral arms often shine with the bluish light of young, hot stars, freshly born from the clouds of gas pressed together by the passing waves. These spiral arms are not fixed in place. Over time, they shift and change, pulled by the complex gravitational forces at work within Andromeda. One important effect comes from the smaller galaxies that orbit Andromeda. These tiny companions tug at the spiral arms, stretch them, and sometimes even twist them, much like the way the moon pulls on the oceans of Earth and causes tides. The result is that Andromeda's spiral arms are always being reshaped, giving the galaxy a lively and changing nature. Andromeda is not alone in space. It is surrounded by dozens of smaller galaxies, which circle around it the way moons circle around planets. Among the most well-known of these companions are two dwarf galaxies named Messier 32 and Messier 110. These smaller systems are not safe in their orbits. They are being slowly torn apart by Andromeda's huge gravity. Piece by piece, their stars and gas are pulled away, adding to Andromeda's own great shape. Over long spans of space-time, some of these dwarfs will likely merge fully with Andromeda, becoming part of its ever-growing body. This process of swallowing smaller neighbours is one of the main ways galaxies grow in size. Orbiting around the central areas of Andromeda are also hundreds of globular clusters. These are tightly packed groups of stars, often containing tens of thousands or even hundreds of thousands of stars all held together by gravity. The stars within globular clusters are usually very old, among the oldest in the entire galaxy. They are like ancient fossils, keeping the memory of Andromeda's earliest years. By studying the stars in these clusters, astronomers can gather clues about the conditions that existed when Andromeda first began to form billions of years ago. In a sense, globular clusters act as historical records written not on paper, but in starlight. Even with all of these known features, Andromeda still has surprises to offer. In recent years, astronomers have found something completely unexpected. A vast thin plane of dwarf galaxies orbiting around Andromeda in an ordered way. Instead of being scattered randomly in space, as current ideas suggest they should be, many of Andromeda's small orbiting galaxies lie within a flat sheet-like structure. This finding has puzzled scientists, since computer models of galaxy formation predict that such satellites should be spread in all directions. Why these small galaxies move in such an organized way remains a mystery, showing that our understanding of galaxy growth may be missing an important piece. Another shocking discovery about Andromeda's past is that it has not always grown gently by swallowing small companions. Proof now shows that Andromeda went through at least one huge crash with another large galaxy in the distant past. This ancient merger shook Andromeda's shape to its core. Stars and clouds of gas were thrown across vast areas of space, reshaping the galaxy's halo, the wide, faint outer region that surrounds the main disk. Even today, the movements of stars in Andromeda's halo carry the sign of this long-ago collision. Remnants of the galaxy that collided with Andromeda still drift in its outer parts, like ghosts of a space battle that ended billions of years earlier. Just as a detective carefully studies every tiny piece of evidence at a crime scene, looking for fingerprints, fibers, or traces of dust to rebuild a story, astronomers act in a similar way when they study distant galaxies. Instead of fingerprints or footprints, however, their clues come in the form of light. When astronomers look at the Andromeda galaxy, they separate its light into different colours, much like how a prism splits sunlight into a rainbow. By studying this spread of light, they can find the presence of different elements. Each element, whether it is hydrogen, oxygen, carbon, or iron, leaves behind a very specific pattern in the light. This pattern is like a chemical fingerprint, and it shows what Andromeda's stars, gas clouds, and dust are made of. The chemical story written into Andromeda's light is not simple or even. It is a record shaped over billions of years, years filled with star births, star deaths, violent explosions, and the endless reuse of cosmic material. Every star that has ever lived in Andromeda has left behind traces of its life, much like generations of people leave behind buildings, tools, or writings that archaeologists study on Earth. Andromeda's chemical makeup, therefore, is a living record of its past. The first thing that astronomers notice is that the most common element in Andromeda is hydrogen. This is not surprising, because hydrogen is also the most plentiful element in the entire universe. It is the simplest of all elements, made from just one proton and one electron. Hydrogen was created in huge amounts in the very earliest moments after the birth of the universe, during the great event that scientists call the Big Bang, which happened about 13.5 billion years ago. Hydrogen is the basic fuel that allows stars to start shining. Whenever a star forms, it begins its life by burning hydrogen in its core, turning it into helium through a process known as nuclear fusion. Alongside hydrogen, helium is also found in large amounts in Andromeda. Like hydrogen, helium was made in those first few minutes after the Big Bang. Together, hydrogen and helium form the basic building blocks from which the very first stars were born. In many ways, hydrogen and helium can be thought of as the cosmic foundation stones. Without them, there would have been no stars, no galaxies, and ultimately no planets or life. But while hydrogen and helium are the most common, they are not what make Andromeda chemically special. What makes this galaxy stand out is the wide range of heavier elements that have slowly been made inside its stars over countless ages. Stars are the true factories of the universe. Deep within their hot cores, nuclear fusion pushes lighter elements together to make heavier ones. Smaller stars like our own Sun can make lighter elements such as carbon, nitrogen, and oxygen. These are elements important for life as we know it. Carbon forms the backbone of molecules in living cells, nitrogen is vital in DNA and proteins, and oxygen allows creatures like us to breathe and use energy. More massive stars, however, are able to go even further. In their short but dramatic lives, They fuse elements into heavier forms such as magnesium, silicon, iron, nickel, and even rarer substances like gold or uranium. When these huge stars reach the ends of their lives, they explode as supernovae. In the fury of these explosions, even heavier elements are formed in just seconds, then thrown out into the galaxy like glitter scattered into the wind. All these newly made elements, whether from smaller stars gently dropping their outer layers or massive stars exploding violently, do not stay locked inside the stars forever. They are released into the space around them, mixing with clouds of gas and dust. From this richer material, new stars are born, and with them new planets can form. Each new group of stars therefore contains slightly more heavy elements than the one before it. Over billions of years, this cycle of birth, death, and rebirth has built up the chemical richness that we see in Andromeda today. But the spread of these elements is not the same everywhere in the galaxy. Astronomers have found that the oldest stars in Andromeda's outer halo, those that formed more than 10 billion years ago, contain very few heavy elements. These ancient stars were born before many of the heavier elements even existed, back in the early days when hydrogen and helium still ruled. In contrast, the younger stars found in Andromeda's spiral arms, where new stars are still forming, are much richer in heavy elements. These regions shine with the presence of metals, which is the word astronomers use to describe all elements heavier than helium. In everyday life, we think of metals as things like iron, gold, or silver, but in astronomy the meaning is broader. For scientists studying galaxies, oxygen, carbon, nitrogen, and all the rest are grouped together as metals because they are products of stellar building. One of the most interesting features of Andromeda's chemistry lies in the unusual amounts of isotopes found there. Isotopes are different versions of the same element. For example, carbon can appear as carbon-12 or carbon-13, depending on how many neutrons are in its nucleus. These small differences are like faint signs left behind by particular processes. Some isotopes are made in the extreme heat and pressure of giant stars, while others are formed more slowly in small stars. By measuring the different amounts of isotopes of elements like oxygen or carbon, astronomers can uncover clues about what kinds of stars added most to Andromeda's makeup. Interestingly, the isotope amounts in Andromeda do not always match those found in our own Milky Way. This suggests that Andromeda and the Milky Way, despite being cosmic neighbours and similar in size, have gone through different histories. Perhaps Andromeda had a faster or slower rate of star formation at certain times. Perhaps it had a greater number of massive star explosions compared to the Milky Way. These differences remind us that even galaxies, like people, each have their own individual life stories, shaped by unique events. Another layer of complexity comes from galactic mergers. Galaxies are not alone. They often crash into and mix with one another. When this happens, a galaxy not only gains new stars but also takes in the chemical fingerprints of the other system. In Andromeda's outer parts, scientists have found patches of stars and gas whose chemical makeup does not match the rest of the galaxy. These areas could be the remains of smaller galaxies that Andromeda swallowed long ago. Although the galaxies themselves have been lost, their chemical signs remain, like faint memories left in Andromeda's outer halo. The central region of Andromeda, its bright glowing core, tells yet another story. Measurements show that the core contains a higher amount of iron and other heavy elements than the areas farther out. This suggests that Andromeda's core went through very strong bursts of star formation in the past. During these times, large numbers of massive stars would have lived and died quickly, exploding as supernovae and enriching the core with heavy elements. The results of that activity remain today, locked into the stars and gas at the heart of the galaxy. Yet even with all this richness, Andromeda still shows a few puzzling features. For example, studies suggest that it has slightly less magnesium than astronomers would expect for a galaxy of its size and age. Magnesium is usually made in massive stars, so its lower amount may mean that Andromeda's history of star formation was shaped by unusual conditions. Perhaps its early environment or its past interactions with other galaxies changed the balance of elements made within its stars. Such mysteries keep astronomers searching, putting together the large puzzle of Andromeda's chemical changes. Dust, too, plays an important role in this story. Spread throughout Andromeda are countless dust grains, each no bigger than a speck of smoke. These grains are made of solid bits of carbon, silicon, oxygen, and other elements. Though tiny, dust grains are essential in the formation of stars and planets. They help cool clouds of gas, allowing gravity to pull the material together to form new stars. they also provide the raw ingredients from which planets are built. Without cosmic dust, worlds like Earth would never have come into being. What is particularly interesting is that the dust makeup in Andromeda is not even. Some regions contain more carbon-rich grains, while others are filled with silicate particles similar to the rocky minerals found on Earth. This difference shows the different processes and environments across the galaxy. In regions where massive stars have lived and died, silicates may be more common, while in quieter areas, carbon grains may build up. Thus, even the dust tells a story about Andromeda's past. Taken together, the chemical picture of Andromeda is like a large tapestry woven over billions of years. Every atom of carbon, every grain of dust, every trace of gold or iron is proof of past events. Some were made in the quiet glow of long-lived stars. Others were made in huge explosions that shook the galaxy. Some were taken from long-gone galaxies that Andromeda swallowed, and all of it together makes Andromeda not just another spiral of stars in the night sky, but a vast and active system with a chemical identity as unique as a fingerprint. One of the most powerful tools that astronomers use to uncover the hidden secrets of Andromeda's chemical makeup is called spectroscopy. This technique is like giving the galaxy a detailed chemical scan, allowing scientists to read its light as if it were a story written in the language of atoms and molecules. Every element in Andromeda, from the simplest hydrogen to heavier elements like carbon, oxygen, and iron, leaves a unique mark in the light it gives off or absorbs. By carefully studying these patterns, astronomers can tell exactly which elements are present, almost like finding the ingredients in a cosmic recipe. Using spectroscopy, scientists have found interesting molecules within Andromeda, including carbon monoxide, which is commonly found in thick, cold clouds where new stars are born. These molecular clouds act like star nurseries, forming the next group of shining stars. Each time astronomers detect these molecules, they are basically catching Andromeda in the act of creating new life in the form of stars. The presence of these clouds tells a story of ongoing change, showing that the galaxy is far from still. It is alive, changing, and always shaping its own future. As Andromeda keeps forming new stars, the makeup of its gas and dust slowly changes. In particular, the galaxy's metallicity, which is the word astronomers use to describe the amount of elements heavier than helium, slowly rises. With each group of stars, heavier elements are made in their cores and released into space when those stars die, enriching the galaxy for the next round of star formation. But this cosmic cycle cannot last forever. As Andromeda slowly uses up its supply of raw gas, the rate at which new stars are born will slowly drop. Over billions of years, the galaxy will move into a quieter stage of life, ruled by older, long-lived stars, with fewer and fewer new stars appearing. Looking even farther into the future, astronomers predict that Andromeda will eventually crash into and join with our own Milky Way galaxy in about 4 billion years. When this huge cosmic meeting happens, the two galaxies will combine their stars, gas, dust, and importantly their chemical histories. The new galaxy will carry the unique chemical marks of both Andromeda and the Milky Way, blending their pasts into a new united identity, a single galactic system that tells the story of billions of years of cosmic change. In this way, the chemical clues that astronomers see today not only show Andromeda's present state, but also give a look into the large unfolding future of our local universe. The Andromeda Galaxy is a huge, bright place filled with a wide variety of stars. From the most ordinary to the most unusual, Andromeda's stars match in many ways what we see in other galaxies spread across the universe. Stars follow life cycles that have been well studied and mapped, and in that sense, Andromeda offers a familiar cosmic landscape. Yet, beyond the shared nature of its billions of suns lies a hidden collection of rare, unusual, and sometimes almost hard to explain stars, each with stories that push our understanding of the cosmos and challenge the models astronomers have carefully developed over centuries. Among the galaxy's most fascinating and mysterious stars are the so-called luminous blue variables, or LBVs. These huge stars are massive stars, often tens or even hundreds of times the mass of our Sun, yet they live life on the edge of stability. Unlike the calmer stars that slowly burn through their hydrogen fuel over millions or billions of years, luminous blue variables exist in a fragile tug-of-war between gravity, which tries to pull their massive bodies inward, and the great pressure from their radiation, which constantly pushes outward. This balance is shaky, and the result is a dramatic, unpredictable life. LBVs can swell to huge sizes, and then, without warning, shed large amounts of their outer layers in violent stellar winds that ripple through space. Their brightness changes in ways that can puzzle observers for decades, sometimes dimming, and at other times shining with the strength of hundreds of thousands of suns. One of the best-known examples in Andromeda is AE Andromedae, a star that has been carefully watched over time as it pulsates, brightens and fades in its short yet spectacular life. These stars take up a short chapter in the life of massive stars, a stage that lasts only a small part of a star's total life, but it is a stage that leads to some of the most dramatic events in the universe, supernova explosions. By studying LBVs like AE Andromedae, astronomers can look into the final unstable moments before a massive star ends its life in a huge outburst, giving clues about processes that shape the chemical makeup of galaxies and even the origin of the elements themselves. Scattered across Andromeda's graceful spiral arms is another notable group of stars known as Wolf-Rayet stars, named after the astronomers Charles Wolf and George Rayet, who first described them in the mid-19th century. These stars are extremely rare, and their appearance shows intense and changing stages of stellar life. By the time a star becomes a Wolf-Rayet, it has already shed much of its outer hydrogen layers, showing the hotter, more energetic cores where heavier elements like helium, carbon, nitrogen and oxygen are actively made. The result is a star of great brightness, giving off powerful blue-white light that can outshine entire star clusters. Yet, with brightness comes instability. These stars are marked by strong, non-stop stellar winds that can strip away large parts of their mass over their short lives, which usually last only a few million years, a mere heartbeat on cosmic timescales. The presence of Wolf-Rayet stars is a cosmic sign, showing places where strong star formation has happened recently, and where the cycle of star birth, change and death continues at a fast pace. Each of these stars is a sign of a future supernova set to enrich the space between stars with heavy elements that will become the building blocks for new stars, planets, and possibly life itself. Among the galaxy's many oddities are hypervelocity stars, a strange phenomenon that stretches the imagination and tests our understanding of gravity. These stars move with such extreme speed that their paths go against what we expect based on normal galactic motion. Some hypervelocity stars may have been part of binary systems where one star exploded in a supernova, violently pushing its partner outward at amazing speeds. Others may have had a close encounter with Andromeda's supermassive central black hole, being thrown outward like cosmic cannonballs by the black hole's huge gravitational pull. These stellar races are not just curiosities, they are messengers carrying information about the forces at work deep within the galaxy. Moving at speeds that could let them leave Andromeda completely, they give astronomers a special way to study the strength of gravitational forces and to map the hidden shape of the galaxy's dark matter halo, which puts a light but constant influence on the motion of stars throughout Andromeda. Farther from the busy arms of Andromeda, in the quieter outer parts of the galaxy, astronomers find a different type of rare star, carbon stars. These stars have an unusually high amount of carbon in their atmospheres, which gives them a strong reddish colour that makes them different from the surrounding stars. The red glow comes from processes deep within the star, where rising currents bring up carbon from the inside and release it into the outer layers. This change affects the star's light, giving it a special colour and making it easy to spot with the right tools. Beyond their beauty, carbon stars play an important part in the cycle of matter. By shedding carbon-rich material into space, they enrich the interstellar medium with the raw materials needed for forming new stars, planets, and even the complex molecules that are the first steps toward life. In this way, carbon stars act as both keepers and sharers of the galaxy's chemical wealth, linking the death of one star to the birth of many others. The centre of Andromeda, its bright central bulge, holds yet another collection of rare stars, extremely metal-poor stars. These ancient suns formed in the galaxy's earliest times when the universe itself was young and heavier elements were few. Unlike stars like our Sun, which contain a rich mix of elements made in many generations of earlier stars, metal-poor stars are leftovers from a time when the universe had barely begun its chemical growth. Their makeup is mostly hydrogen and helium, with only tiny amounts of heavier elements. Because of this, these stars give astronomers a direct look into the conditions of the early universe acting as living fossils that show what Andromeda and galaxies across the cosmos may have looked like billions of years ago. Many of these metal-poor stars are among the oldest objects in Andromeda, possibly dating back to when the galaxy itself was first forming, and their study helps scientists rebuild the timeline of star formation and galaxy growth through cosmic history. In contrast to these ancient leftovers are stars caught in short, changing stages of their life, such as yellow supergiants. These stars sit in a rare and short phase, standing between red supergiants and blue supergiants. The change is so short that, in astronomical terms, it is almost instant, a mere few thousand years out of a life that can last millions or even tens of millions of years. This shortness makes yellow supergiants very hard to observe, yet each discovery gives important insight into the life cycles of massive stars. By studying these short-lived stars in Andromeda, astronomers can improve their models of stellar evolution, understanding more clearly how stars change in colour, size and brightness as they move through different stages of life. The presence of yellow supergiants in Andromeda's group of stars adds another layer to the galaxy's story, reminding us that every star, no matter how brief its time, adds to the ongoing story of the cosmos. Among the most mysterious and extreme objects in Andromeda are magnetars, a rare type of neutron star with magnetic fields so powerful that they are almost beyond human understanding. Formed from the collapsed cores of massive stars that exploded as supernovae, magnetars are incredibly dense, packing the mass of the Sun into a sphere barely 20 kilometers across. Their magnetic fields can be trillions of times stronger than Earth's, able to twist space around them and create bursts of high-energy radiation that ripple across the galaxy. The finding of magnetars in Andromeda shows that the galaxy has had many supernova events, each leaving behind remains with extreme physical properties. By studying these objects, scientists can explore physics at extremes impossible to recreate in labs on Earth, giving a window into how matter and energy behave under conditions that push the very limits of our understanding. Adding even more variety to Andromeda's group of stars are variable white dwarfs. These small, dense leftovers of dead stars often show surprising changes in brightness. Some of these changes come from pulsations within the star itself, while others come from interactions with nearby material, especially if the white dwarf is part of a binary system. In such cases, the white dwarf may slowly pull matter from its partner, leading to dramatic outbursts known as novae. During a nova, the white dwarf can brighten by thousands of times for a short period, only to slowly fade back into relative dimness. Each of these events gives astronomers valuable information about stellar life cycles, binary star behavior, and the processes that control nuclear fusion in extreme conditions. Taken together, all these rare and unusual stars show a picture of Andromeda that is far richer and more complex than what meets the eye from Earth. They are not just oddities or curiosities, they are key clues to the galaxy's history and its ongoing growth. By observing luminous blue variables, Wolf-Rayet stars, hypervelocity stars, carbon stars, metal-poor ancient stars, yellow supergiants, magnetars, and variable white dwarfs, astronomers can piece together the processes that control star formation, stellar death, chemical enrichment, and the movement of the galaxy. Each star acts as both witness and participant in the grand cosmic story, tracing paths that connect the galaxy's earliest moments to its possible future. Even within a galaxy as well studied as Andromeda, new discoveries continue to surprise and challenge astronomers. Tools on the ground and in space are revealing faint stars once hidden by dust or outshone by their neighbours. Advanced spectroscopic techniques allow scientists to measure the chemical signs of stars, spotting small differences in makeup that hint at unusual life histories. Observations across the electromagnetic spectrum, from radio waves to gamma rays, are uncovering strong stellar winds, explosive events, and high-energy actions that were once thought impossible. And with every new observation, theories are improved, models updated, and our understanding of the galaxy's complex workings becomes just a little deeper. The study of Andromeda's rare stars is not just an academic task. These celestial objects play important roles in the galaxy's life story, driving chemical change, shaping interstellar environments, and affecting the formation of future generations of stars and planetary systems. Luminous blue variables shed their outer layers to enrich their surroundings with heavy elements. Wolf-Rayet stars give off intense radiation, and winds that shape the nearby interstellar medium. Hypervelocity stars trace the influence of strong gravitational forces and reveal the hidden design of the galaxy. Carbon stars act as chemical gardeners, spreading space with the materials needed for new stars and planets. Magnetars and variable white dwarfs give natural laboratories for extreme physics, showing processes that no human experiment can recreate. Even the ancient metal-poor stars tell stories of a universe in its early years, giving astronomers direct insight into conditions billions of years ago. In many ways, these hidden bright stars are the unsung heroes of Andromeda, often overlooked in broad surveys or simple discussions of galaxies, which tend to focus on bright star clusters or the big spiral arms. Yet without these unusual and rare stars, the picture of Andromeda would be incomplete. They show the violent, the short-lived, the extreme, and the ancient, all parts of a galaxy that is alive with activity and full of history. Their presence reminds us that even a galaxy as close and familiar as Andromeda still holds secrets waiting to be uncovered, mysteries that stretch the imagination and challenge our understanding of the cosmos. Andromeda's rare stars scattered across its core, spiral arms and outer edges are more than scientific curiosities. They are chapters in a story that spans billions of years, a story of birth, change and eventual death that is seen in galaxies across the universe. Each type of star, from the active luminous blue variables to the short-lived yellow supergiants, from the blazing Wolf-Rayet stars to the ancient metal-poor leftovers, adds a unique line to this cosmic story. By studying them, astronomers not only learn about Andromeda's past and present, but also gain a window into the forces that shape all galaxies, including our own Milky Way. These stars are teachers, guides, and witnesses, showing us how matter is made, how energy flows, and how gravity controls the dance of the cosmos. As telescopes grow more powerful, as tools more sensitive, and as computer models more advanced, the galaxy continues to reveal its hidden wonders. Stars once invisible become visible. Processes once mysterious become understood. Andromeda, though studied for centuries, still holds surprises. Each observation of a hypervelocity star, a carbon star, a magnetar, or a variable white dwarf adds a piece to the cosmic puzzle, showing not just how stars live and die, but also how galaxies grow, interact, and affect the wider universe. In this way, the study of Andromeda's rare and unusual stars is a journey into the heart of cosmic understanding, a journey that stretches across space and time, inviting humanity to explore, to question, and to marvel at the amazing variety of life in the universe, even when that life is made of blazing balls of gas, dense leftovers of dead stars, and the most extreme forms of physics itself. Andromeda is not just a group of stars spread randomly across space. It is a huge, impressive cosmic city where stars do not live alone but gather in busy communities, forming connected groups that change together over millions or even billions of years. Picture looking up at a wide area filled not just with single points of light, but with neighborhoods of stars, each with its own story, past and special behavior. These neighborhoods, or star clusters as astronomers call them, come in many types, each showing a stage of star life, galaxy growth, and the cosmic forces that shape whole galaxies. Among the most interesting groups of stars in Andromeda are the globular clusters. These dense, almost round groups of stars are among the oldest structures in any galaxy, often containing stars that were born in the early universe just hundreds of millions of years after the Big Bang. While stars in our own Milky Way also form such clusters, Andromeda has far more. Astronomers estimate that over 500 globular clusters orbit Andromeda, forming a halo around the galaxy like a shining necklace. Each of these clusters is like a time capsule, keeping the conditions of a universe that existed billions of years ago. However, not all globular clusters in Andromeda fit expectations. While many have the oldest stars, astronomers have found some clusters that seem surprisingly young. These younger stars challenge normal ideas about how clusters form, showing that star birth can sometimes happen in ways thought impossible for such tightly packed groups. Even more surprising, some clusters move in unusual paths, suggesting they might not have started in Andromeda at all. Evidence shows these clusters were probably captured from smaller galaxies that collided with Andromeda long ago, adding their stars to the galaxy's growing population. In this way, Andromeda's globular clusters are not just relics of old times, but also records of past collisions, showing the galaxy's history through their orbits and makeup. Beyond the classic globular clusters, Andromeda has a wide variety of extended clusters. Unlike the dense globular clusters, these are looser, with stars spread more thinly, yet still held together by gravity. Extended clusters are somewhere between regular star clusters and small galaxies. Their lower density and loose structure suggest they could show stages of galaxy growth, giving clues about how small galaxies are slowly absorbed and changed by larger ones. These clusters show that cosmic structures can be flexible, blurring the line between a star cluster and a small galaxy. Adding to the mystery, Andromeda has faint fuzzy clusters, a strange type of star group. They were first found in the galaxy's distant outer areas, and they do not fit simple categories. While they share some traits with globular clusters, like having old stars, they are more spread out and loosely organized. This makes them fragile in Andromeda's gravity, raising questions about how they survived billions of years without being torn apart. Some scientists think these faint fuzzy clusters may be leftover parts of small galaxies that merged with Andromeda long ago, slowly spreading into their current fragile forms. These clusters act as ghostly witnesses to old galactic collisions, quietly preserving evidence of Andromeda's changing past. Yet the story of Andromeda's star clusters does not end with the old and strange. The galaxy also has surprisingly young and big clusters, filled with bright, hot stars that formed only a few million years ago, a blink of an eye in cosmic time. What makes these young clusters interesting is where they are located. Many are in areas where astronomers thought star formation had stopped long ago. Far from Andromeda's main star nurseries, their presence shows that new stars can still form under unusual conditions, perhaps triggered by gravitational effects from nearby small galaxies or past collisions. These young clusters are like a living lab for understanding how star formation can continue even in calm areas of a galaxy, going against earlier ideas about where new stars appear. The chemical makeup of Andromeda's star clusters adds more intrigue. Not all clusters have the same chemical mix as the galaxy's stars overall. Some have stars with unusual amounts of metals. Astronomers call elements heavier than hydrogen and helium metals. A few clusters even have compositions like those in smaller dwarf galaxies, rather than a big spiral galaxy like Andromeda. These chemical differences act like fingerprints, showing past events where Andromeda absorbed smaller galaxies and added their stars and clusters to itself. By studying the chemistry of these clusters, astronomers can piece together a timeline of mergers, going back billions of years to understand how the galaxy grew. The placement of Andromeda's star clusters gives more clues about the galaxy's past. Some clusters are in spots where gravity should have torn them apart long ago, but they still exist, hinting at unusual formation histories or interactions that helped them survive. Other clusters are arranged in streams or arcs, showing signs of past galactic mergers. These patterns suggest that Andromeda's halo, the large spherical area around the galaxy, is still shaped by gravity from smaller galaxies and remnants of past collisions. The positions of clusters are not random. They hold records of Andromeda's past and ongoing growth, showing a galaxy that constantly changes and reuses its stars. Even among this diverse group, some of Andromeda's clusters are hard to classify. Some contain very big stars that should not have lasted billions of years, or mixes of stars that seem to go against expected ages and life paths. These unusual clusters may be temporary, loosely held together by gravity and eventually spreading into Andromeda's general star population. These temporary clusters give a view into the delicate balance of forces that keep star clusters together, and the complex movements of stars inside a galaxy. Better telescopes have also revealed more of Andromeda's clusters, showing groups that were hidden before. Dense areas near the galaxy's centre, once blocked by dust and bright nearby stars, now show clusters that could give key information about the galaxy's central supermassive black hole. Interactions between these clusters and the black hole's strong gravity could change both the cluster's structure and the movement of stars near the galaxy's centre. Likewise, clusters far from the galaxy's main body challenge astronomers to rethink how far Andromeda's gravity reaches. These distant clusters give clues about how galaxies interact with space around them and the invisible forces holding cosmic structures together. The amazing variety of clusters in Andromeda shows the galaxy's complex and active nature. Each cluster, from dense ancient globular clusters to loose faint fuzzy clusters, tells a story of formation, survival, and sometimes cosmic disruption. The clusters act as living records, keeping the history of Andromeda's interactions with other galaxies, star births and deaths, and the ongoing gravity that shapes its structure. By studying these star groups, astronomers learn not just about the life of stars, but also about how galaxies form and change on a cosmic scale. The star clusters of Andromeda also show the connection between time and gravity. Globular clusters show how stars born billions of years ago can stay together despite strong gravity. Extended clusters and faint fuzzy clusters show the delicate balance needed for stars to stay together for long periods, revealing how small effects from nearby galaxies or internal shifts can slowly change or even break them. Young big clusters, on the other hand, show the galaxy's ongoing activity, highlighting areas where stars can still form, even in calm regions. Some clusters also mark past dramatic events. Streams of stars, faint arcs, and unusual chemical makeup all point to mergers that left lasting marks on Andromeda. This shows that the galaxy's halo is not fixed. It is an active area where remains of smaller galaxies continue to mix with the bigger system. The movement and layout of star clusters carry information about past collisions, mergers, and absorption events that shaped the galaxy over billions of years. Even the outliers, clusters that are hard to classify or have unusual stars, give important clues about galaxy growth. Some may be temporary groups that eventually spread out. Others may have formed under unusual conditions, influenced by gravity or past collisions that triggered intense star formation far from the galaxy's center. Each unusual case challenges astronomers to improve their understanding of how stars and galaxies change, showing the universe is far more complex than any simple model can capture. Studying Andromeda's star clusters is not just about listing cosmic curiosities. Each discovery adds to understanding how galaxies form, change, and interact with their surroundings. Clusters show processes over billions of years, revealing both stability and fragility in star groups. They show the link between formation, gravity, chemical change, and galaxy mergers. By studying these clusters carefully, astronomers can rebuild Andromeda's history step by step, uncovering a story spanning much of the universe's life. In the grand view of the universe, Andromeda is both a lab and a history book. Its star clusters are chapters in an ongoing story, recording the birth, life, and death of stars, the addition of smaller galaxies, and the constant reshaping of cosmic structures. From the oldest, densest globular clusters to the youngest, brightest massive clusters, Andromeda shows the incredible variety and complexity of star groups. Each cluster gives a different view, a unique way to understand the forces that shape galaxies and the universe as a whole. At the very center of the Andromeda galaxy, hidden deep within its bright core, is one of the most mysterious and powerful objects in space, a supermassive black hole. This amazing object is not just another part of the galaxy. It is a force that shapes everything around it, affecting the movement of many stars, bending light itself, and pulling in any matter that gets too close to its strong gravity. For decades, scientists have thought that most large galaxies, especially ones as big and spread out as Andromeda, have such huge black holes at their centers, but studying them closely is still difficult. Still, observations of Andromeda have shown the enormous size of its central black hole, named M31 star, which is thought to weigh about 140 million times the mass of our Sun. To compare, this makes it much bigger than the supermassive black hole at the center of our own Milky Way galaxy, known as Sagittarius A star, which, while huge, is small next to M31 star. The presence of such an enormous object at Andromeda's center raises big questions for astronomers. How did a single black hole grow so large? How did it come to control the gravity of one of our closest galactic neighbors? Many popular ideas suggest that Andromeda did not grow alone. Over billions of years, it probably absorbed smaller galaxies, each bringing its own black hole. Through a series of mergers, these smaller black holes may have combined, eventually forming the supermassive black hole we see today. Each merger would have released large amounts of energy, stirring the galaxy and changing the orbits of stars and gas clouds inside it. Around M31 star is another noticeable feature, a dense, tight group of stars. Unlike the more spread-out star clusters in some galactic centers, this group is packed closely together and moves in ways that are extreme even for galaxies. The stars in this group orbit very fast, pulled around by the black hole's strong gravity. By carefully watching the paths and speeds of these stars, astronomers were able to confirm the presence of M31 star. No other object or group of objects could explain the fast movements seen in this central cluster. In this way, the stars act as signs, showing the hidden presence of an object that cannot be seen directly because it swallows light as well as matter. Even though it is extremely heavy, Andromeda's central black hole does not seem to be eating large amounts of matter right now. In many galaxies, supermassive black holes are surrounded by what astronomers call an active galactic nucleus, or AGN, where gas, dust, and sometimes entire clouds of matter fall inward, heating up as they go and giving off strong radiation that can be detected from far away. But M31 star is fairly quiet. It gives off only small amounts of X-rays and radio waves, and no major bursts of energy have been seen. Scientists think this calm state may not last forever. In the past, the black hole may have been much more active, feeding on gas and dust nearby, releasing energy that could have affected the development of Andromeda's center. Similarly, future encounters with clouds of gas, groups of stars, or even whole smaller galaxies could wake M31 star again, turning it into a more active, bright and energetic object that could change the galaxy's center. The supermassive black hole at the center is not the only kind of black hole in Andromeda. Astronomers think that smaller, medium-sized black holes are scattered through the galaxy, hidden in its spiral arms and star clusters. These medium black holes, with masses from a few hundred to several thousand times the mass of the Sun, probably formed in one of two ways, either from the collapse of very big stars at the ends of their lives, or by slowly merging smaller black holes over time. While supermassive black holes rule the centers of galaxies, these medium black holes are much harder to find, and spotting them needs very sensitive instruments and careful watching. They may hide in the centers of dense star clusters, or move around the galaxy's disk, quietly affecting the stars near them with their gravity. There is growing evidence that some of Andromeda's globular clusters, round groups of stars held together, may have black holes at their centers. In these areas, a single black hole, or even several, could quietly control the movement of nearby stars. If true, these medium black holes could help explain how supermassive black holes grow. Repeated mergers of smaller black holes over millions or billions of years might slowly build bigger black holes, eventually creating objects as huge as M31 star. In this way, the galaxy may have a moving system of black holes, from small to unimaginably large, all affecting each other with gravity. Some black holes do not stay in one place but move around the galaxy. These wandering black holes could be leftovers from smaller galaxies that Andromeda swallowed long ago, thrown out of place by gravity during collisions. Others may have been pushed out of dense clusters after encounters with other massive objects. Even though they cannot be seen, they give off no light. These moving black holes still affect the galaxy around them. Their gravity can change the orbits of nearby stars, affect the formation of planetary systems, and even disturb the paths of star clusters. In this way, Andromeda may be a natural lab of hidden forces, with many black holes shaping its structure from the shadows. Finding these black holes is hard. They show themselves only indirectly, through their effects on gravity. Sometimes, a black hole passing in front of a distant star will bend and magnify the star's light, an effect called gravitational lensing. Watching these events allows astronomers to guess the presence and mass of these hidden objects, giving rare views of something otherwise invisible. New technology, especially in detecting gravitational waves, gives more chances to find hidden black holes. When black holes merge, they send ripples through space and time, gravitational waves, that can be measured with sensitive instruments on Earth. By catching these signals, scientists hope to map Andromeda's hidden black holes, finding their locations, sizes, and interactions. The role of black holes in Andromeda's growth is very important. Even though they cannot be seen directly, they have shaped the galaxy over billions of years. The supermassive black hole at the center controls the motion of stars in the inner core, while medium and wandering black holes quietly affect the orbits of stars and clusters farther out. In some cases, black holes may cause new stars to form by squeezing gas clouds with their gravity, while in other cases, they may stop star formation by scattering gas away. This shows the complex role black holes play in shaping galaxies. Studying Andromeda's black holes also helps us understand our own galaxy. Sagittarius A star, the Milky Way's central black hole, is similar to M31 star but smaller and quieter. Comparing the two helps astronomers explore why some black holes grow so big while others stay smaller, and why some black holes become active while others stay quiet. By studying these cosmic cousins, scientists can begin to understand the bigger story of galaxy formation and growth in the universe. The central black hole, M31 star, also tells the violent history of Andromeda. Theories say that billions of years ago, Andromeda collided with and absorbed smaller galaxies, each collision stirring stars, gas and dust and helping the supermassive black hole grow. The tight cluster of stars around the black hole may hold remains of these ancient mergers, star groups pulled toward the center by the black hole's gravity. Every orbit of a star in this cluster, every bend in light near the black hole, shows a story of cosmic change, revealing how Andromeda became the spiral galaxy we see today. Even now, the story of Andromeda's black holes is not finished. Future collisions with other galaxies, interactions with dense gas clouds, and finding more medium or wandering black holes could change the galaxy again. Astronomers keep watching, studying, and simulating the movements of stars and gas, slowly uncovering the hidden forces shaping one of the universe's closest neighbours. In doing this, they are learning not only about Andromeda, but also about black holes, galaxy growth, and the way matter and gravity interact over billions of years. Andromeda is not just a group of stars in a spiral pattern. It is a living, changing system, with supermassive, medium and wandering black holes acting as invisible guides, shaping the formation and movement of stars and clusters, controlling the flow of gas and dust, and affecting the galaxy's future. As technology improves and new telescopes and detectors are used, astronomers will discover even more about these mysterious objects. Every observation adds a piece to the puzzle, helping us understand how black holes grow, how they interact, and how they quietly but strongly influence the large structures we see in space today. Without dark matter, the Andromeda galaxy, along with our own Milky Way and countless other galaxies spread across the universe, would not exist in the forms we see today. The universe as we know it would look very different. Stars would not have gathered into the huge spiral arms that decorate galaxies, planets would be far less likely to orbit in steady paths, and the detailed cosmic dance that shapes galaxies would be broken. Dark matter, though invisible and mysterious, acts as the hidden framework that allows galaxies to form, grow, and last for billions of years. It is the unseen glue, the quiet builder, whose gravitational pull holds the bright matter, the stars, planets, gas clouds, and dust together. One of the first clues that Andromeda, also called Messier 31, is dominated by dark matter came from careful observations of how the galaxy spins. When astronomers measured the speeds of stars and gas in Andromeda, they found something surprising. According to normal physics, if Andromeda had only the stars, gas and dust we can see, the outer parts of the galaxy should spin much more slowly than the inner parts. Imagine a merry-go-round where the horses near the centre spin fast while those on the edge hardly move. That is what scientists would expect if only visible matter were there. Yet, in Andromeda, stars at the far edges were moving very fast, as if pulled by a gravity much stronger than what the stars and gas alone could provide. The simplest explanation for this strange rotation is that Andromeda is surrounded by a huge halo of invisible material. This halo goes far beyond the glowing spiral arm seen in telescopes and contains much more mass than all the stars, planets, and clouds of gas combined. The gravity of this unseen substance is so strong that it keeps the galaxy together, stopping it from flying apart even though its outer stars move quickly. Scientists think that the total mass of dark matter in Andromeda is likely several times bigger than all the visible matter. Without it, the galaxy's stars and gas clouds would not have enough combined gravity to stay together, and Andromeda as we know it would not exist. Dark matter in Andromeda is not spread evenly like a smooth fog. Instead, it seems uneven, forming areas of different density across the halo. Some parts of the halo have thicker concentrations, while others are thinner. Astronomers have started to map this hard-to-see material using a method called gravitational lensing. This method looks at how light bends as it moves through the gravity field of massive objects. When light from distant stars or galaxies passes through Andromeda's halo, it bends slightly, as if the invisible mass is pulling on it. By carefully measuring these changes, scientists can make a map of dark matter in Andromeda, showing its lumpy and irregular structure. The clumps of dark matter in Andromeda may have been shaped by many factors. Some probably formed through interactions with smaller satellite galaxies orbiting Andromeda. As these dwarf galaxies move through the halo, their gravity could have pulled and twisted patches of dark matter, creating a pattern of denser and lighter areas. Also, the forces inside Andromeda itself, the pull of its stars, the tug of gas clouds, and the motion of spiral arms, may have shaped the dark matter over billions of years. The result is a halo that is far from even, a changing and evolving structure invisible to the human eye but deeply shaping the galaxy. Dark matter does more than shape Andromeda inside, it also affects the galaxy's relationship with nearby galaxies. Andromeda is a main member of the Local Group, a collection of galaxies that includes the Milky Way, the Triangulum Galaxy, and dozens of smaller satellite galaxies. The gravity of dark matter reaches far beyond Andromeda's bright edges, extending into space between galaxies and gently pulling on nearby galaxies. Some dwarf galaxies, quietly orbiting Andromeda, are held in place by the gravity of this dark halo, stopping them from drifting away into empty space. Others are slowly being pulled in, spiraling toward the larger galaxy, drawn by the hidden mass that dominates the halo. One of the biggest mysteries about dark matter in Andromeda is the distant future, when Andromeda and the Milky Way are expected to collide in about 4 billion years. The collision of two such huge galaxies will be a cosmic show. The visible stars and gas clouds in both galaxies will interact violently, producing shock waves, forming new stars and changing the shapes of the galaxies. Yet the dark matter will act differently. Unlike the bright matter, which can collide, compress, and create new events, dark matter does not interact with light or electricity. It passes through itself, and ordinary matter almost completely unhindered. During the collision, the dark matter halos of Andromeda and the Milky Way will pass through each other, their strong gravity pulling on stars and gas and helping shape the final galaxy. The way dark matter behaves during this collision gives important clues about its true nature. Many scientific theories suggest that dark matter is made of weakly interacting particles. If this is true, its pattern after the collision could show the particle properties of dark matter, like mass, speed, or how these particles respond to gravity. On the other hand, if dark matter interacts even a little with itself, astronomers may see unexpected patterns in how the merged halos settle. Studying these results could help separate different theories and bring us closer to understanding one of the universe's deepest mysteries. Another big question about dark matter is its origin. Did it form with the first stars and galaxies, or did it exist earlier, creating invisible structures for ordinary matter to gather on? Many researchers think dark matter was created in the earliest moments of the universe, just after the Big Bang, about 13,800 million years ago. In those early times, dark matter particles may have spread across space, creating gravity wells where ordinary matter later fell. These invisible wells would act as foundations for the first galaxies, including Andromeda, long before any stars started burning. Other theories suggest dark matter could be connected to unknown forces or particles. While the standard model of particle physics explains ordinary matter, it cannot explain dark matter. Its existence points to things beyond our current knowledge, possibly hinting at a hidden part of physics with its own particles and rules. So, mapping the dark matter in Andromeda is more than a study of one galaxy. It is exploring the basic rules that govern the universe. By seeing how stars, gas, and small galaxies respond to dark matter's gravity, astronomers hope to learn its properties and maybe find the particles behind it. Besides its gravity, dark matter indirectly shapes the life of stars and the growth of galaxies. By providing most of the galaxy's mass, it stabilizes the galaxy's rotation, keeping the balance that lets spiral arms last for billions of years. Without this balance, spiral arms could fall apart, star formation could slow or become chaotic, and the galaxy might take on a more irregular shape. The lumpy nature of dark matter could also affect local star formation. Denser regions may slightly increase the density of gas clouds, encouraging them to collapse and form new stars. Though invisible, dark matter is present in every part of galactic evolution, quietly guiding processes that might seem random. The study of Andromeda's dark matter uses several advanced methods. Gravitational lensing is one of the strongest tools, letting astronomers detect the bending of light caused by unseen mass. Scientists also track the speeds of stars and satellite galaxies, using their motion to guess the halo's mass and shape. Computer models are also important. By modelling Andromeda with different dark matter ideas, researchers can test how different distributions, particle types, and interactions affect the galaxy's structure and growth. Comparing these models to real observations helps scientists narrow down possibilities and improve their understanding of dark matter. Dark matter's influence goes further, affecting interactions inside the local group. The gravity of Andromeda's halo affects not only its nearby satellites, but also the larger dynamics of the group. For example, the Milky Way is slowly moving toward Andromeda, and the two galaxies will eventually merge. The unseen mass of both galaxies affects their paths, speeds, and the timing of the collision. Similarly, smaller galaxies in the local group are constantly influenced by dark matter's gravity, sometimes being captured into orbit around larger galaxies or pushed onto new paths through space between galaxies. Despite decades of study, dark matter remains one of the most fascinating mysteries in astrophysics. Its presence is shown through its gravity, yet it cannot be directly detected. Experiments on Earth have not yet found dark matter particles, and even their basic properties, mass, makeup, and type of interaction, are still mostly unknown. Yet its influence is clear. In Andromeda, dark matter is the invisible builder of the galaxy's shape, the hidden hand controlling its spin, and the unseen force guiding its interactions with nearby galaxies. Without it, Andromeda would be just a scattering of stars, unable to form the huge, spiraling masterpiece we see across space. Studying dark matter in Andromeda is more than looking at a single galaxy. It is a journey into the hidden structure of the universe. By seeing how this invisible matter shapes stars, gas, and satellite galaxies, scientists hope to put together a fuller picture of cosmic history. Future missions and observations may show whether dark matter formed in the universe's first moments, or if it is linked to unknown forces and particles. Through careful mapping of Andromeda's halo and study of its interactions, humans may one day reveal this mysterious part of the universe. Dark matter, though unseen, is essential to Andromeda and every galaxy like it. It holds stars and gas together, guides galaxy rotation, affects interactions with neighbouring galaxies, and plays a key role in shaping the universe over billions of years. The quest to understand dark matter in Andromeda is not just about mapping an invisible halo. It is about discovering the hidden forces that shape reality, exploring the origins of galaxies, and seeking answers to questions that go back to the beginning of time. Mapping the galaxy of Andromeda is no easy task. Even though it is the closest large galaxy to our own Milky Way, it gives astronomers a challenge because of its huge size. Andromeda, often called M31 in the list of galaxies, stretches across a wide area of space, measuring roughly 220,000 light-years across. To put this into perspective, the Milky Way itself is about 150,000 light-years across, which means that Andromeda is clearly bigger. Looking at such a massive structure as a whole is not as simple as pointing a telescope and taking one photo. The galaxy just does not fit neatly inside the view of most telescopes. Even the strongest instruments, whether on Earth or orbiting above it, can only capture small parts of the galaxy at a time. As a result, astronomers must take hundreds, sometimes thousands, of separate pictures and carefully put them together to make a full image. This careful process is not quick. It takes years of careful watching, data work, and precise alignment, as each piece must match exactly with its neighbours. One of the most amazing achievements in this effort came from the Hubble Space Telescope, which has given some of the most detailed views of Andromeda ever recorded. Hubble can capture extremely sharp images, much clearer than what is possible with ground-based telescopes, because it is above Earth's atmosphere. To map Andromeda, scientists told Hubble to take thousands of separate shots, each showing a small part of the galaxy. These shots were then joined into a huge mosaic, showing millions and millions of stars scattered across Andromeda's spiraling arms and central bulge. The resulting image is not just beautiful, it is full of scientific information. Every point of light in the mosaic represents a star cluster, or sometimes a distant background galaxy. The level of detail lets astronomers study the traits of individual stars, look at their life cycles, and see how they are spread across the galaxy. However, mapping Andromeda involves more than just taking pictures. Photos alone cannot tell the full story of this complex galaxy. To really understand Andromeda, astronomers must also measure distances, study motions, and find out the chemical makeup of its stars, gas, and dust. One of the most useful tools for this type of study is spectroscopy. Spectroscopy involves splitting the light from a star or gas cloud into its basic colours, or wavelengths, much like a prism makes a rainbow from sunlight. By looking at the resulting spectrum, scientists can find specific chemical elements, estimate the temperature of stars, and even see how fast gas and stars are moving toward or away from Earth. In other words, spectroscopy lets astronomers read the fingerprints of space objects. It shows the makeup of Andromeda's regions, pointing out where the galaxy has clouds rich in hydrogen, carbon, oxygen, or more unusual elements made in the cores of older stars. These chemical clues also tell a story about the galaxy's history, where stars have formed, where they have died, and how material has been reused to make new stars. Motion mapping is another important part of understanding Andromeda. The galaxy is not still. It is a living system, always turning and changing under the pull of its own gravity and that of nearby galaxies. The stars in Andromeda's spiral arms move around its central bulge at different speeds. Some areas, especially near the core, spin faster, while outer areas move slower. To track these motions, astronomers use something called the Doppler effect. This effect, known to anyone who has heard the changing pitch of a passing siren, happens when the wavelength of light changes depending on whether an object is moving toward or away from the viewer. Light from stars moving toward Earth is slightly compressed, looking bluer, while light from stars moving away stretches out, looking redder. By measuring these small shifts across many stars and gas clouds, scientists can make a detailed rotation map of Andromeda. These maps not only show how the galaxy turns, but they also reveal gravitational effects, interactions with smaller galaxies, and signs of past galaxy collisions. While motion and makeup give key information, seeing Andromeda is also made harder by interstellar dust. Dust particles are tiny, but they scatter and block light, hiding big parts of the galaxy when seen with normal telescopes. Some of Andromeda's densest areas are almost completely hidden to regular optical telescopes, leaving gaps in our knowledge. To look through these cosmic veils, astronomers use infrared telescopes, which see longer wavelengths of light that can go through dust clouds. The Spitzer Space Telescope, for example, mapped Andromeda in infrared light, showing dust-heavy regions that were hidden before. These observations show where new stars are forming, as dust clouds often hold the material needed for starbirth. In these dense areas, gas collapses under gravity to start nuclear fusion, making new stars that may later shine across the galaxy. Andromeda's makeup goes beyond stars and dust to huge areas of hydrogen gas. Hydrogen is the most common element in the universe, and it gives off a certain type of radio wave that radio telescopes can detect. This lets astronomers map gas even in areas where visible light is blocked. By charting hydrogen clouds, scientists learn about the galaxy's future potential for star formation. Dense gas areas show where new stars might form, while thinner areas suggest regions that may soon run out of material. These gas maps also show the galaxy's structure on a large scale, tracing spiral arms and the outer disk with great detail. Advances in computer modelling have changed how Andromeda is studied. Observations alone, while very helpful, cannot always show the full complexity of a galaxy, with hundreds of billions of stars. Astronomers now use computer simulations to recreate Andromeda in virtual space, including known features like the spread of stars, the effect of dark matter, and gravity interactions with other galaxies. These simulations let scientists test different ideas for how Andromeda formed and changed. By comparing the simulated galaxy with real observations, astronomers improve their models, getting a better understanding of the processes shaping Andromeda. For example, simulations can show how spiral arms keep their shape, how star formation is controlled, and how past mergers with smaller galaxies have left marks in the star distribution. Speaking of mergers, Andromeda's small companion galaxies are an important part of the mapping process. The galaxy is surrounded by a family of smaller galaxies, some easily seen, like M32 and M110, while others are faint and hard to find. Large surveys of the sky have found a whole system of dwarf galaxies orbiting Andromeda. Tracking these companions is important for understanding the galaxy's gravitational pull and history. Dwarf galaxies often fall into their larger host, slowly being absorbed over billions of years. By studying these interactions, astronomers learn how big galaxies grow, how stars mix, and how dark matter shapes galaxy halos. Among the most ambitious mapping projects is understanding Andromeda's future collision with the Milky Way. Current measurements of its motion show that Andromeda is moving toward our galaxy at about 120 kilometers per second. In around 4.5 billion years, the two galaxies are expected to start merging in a dramatic cosmic event. Scientists use detailed observations of stars, gas clouds, and small galaxies to make computer models, predicting how this merger will happen. The simulations show that over billions of years, the spiral shapes of both galaxies will be broken, stars will move into new orbits, and a new, larger galaxy, sometimes called Milkomeda, will form. This future event shows why it is important to understand Andromeda not just as it is today, but as a changing system with a story still unfolding. Even after decades of observation and modelling, many mysteries remain. Some parts of Andromeda are still not well understood, whether because they are hidden by dust too faint to see, or affected by unseen forces like dark matter. New technologies will be needed to uncover these hidden secrets. Future space telescopes, including the upcoming Nancy Grace Roman Space Telescope, are expected to expand our knowledge. With stronger instruments able to capture incredible detail, astronomers will be able to study individual stars, find previously hidden structures, and improve models of Andromeda's formation and growth. These improvements will not only increase our understanding of Andromeda, but also give wider insight into how galaxies behave across the universe. The work of mapping Andromeda shows the size, patience, and creativity needed for modern astronomy. It is a project that combines advanced technology, careful watching, theory work, and years of careful analysis. Each image, spectrum, and simulation adds to a clearer picture of a galaxy that is both familiar and mysterious. As astronomers continue to map Andromeda's stars, dust, gas, and companions, they piece together not just the story of one galaxy, but also the bigger story of cosmic evolution. From the glow of newborn stars in dusty nurseries to the wide spiral arms stretching tens of thousands of light years, Andromeda gives a window into how the universe works on its larger scales. In mapping Andromeda, scientists are not just taking pictures. They are tracing the unseen threads of gravity, makeup, and motion that hold the galaxy together. They measure the faint light that has travelled millions of years to reach Earth, read the chemical fingerprints of stars formed billions of years ago, and simulate the dance of galaxies that will happen billions of years from now. Each discovery raises new questions, showing the galaxy's layers of complexity and hinting at things that may challenge our current ideas of physics and the universe. Andromeda's story is also a story of connection. Its interactions with small companion galaxies, the future merger with the Milky Way, and the flow of gas and dust all show that galaxies are not isolated islands, but part of a huge, connected cosmic web. Mapping these interactions needs teamwork across continents and the use of many observatories, from ground-based radio telescopes to space-based infrared and optical tools. The effort shows human curiosity and creativity, proving how careful observation, measurement, and modelling can reveal the secrets of a galaxy millions of light-years away. In the coming decades, as new telescopes are launched and computer power grows, our maps of Andromeda will become even more detailed. Astronomers will be able to zoom in on individual stars, find the faintest dwarf galaxies, and maybe even see the earliest moments of star formation in its distant spiral arms. These advances will not only improve our understanding of Andromeda itself, but also give key points for understanding galaxies across the universe, giving clues to the origins, growth, and future of galaxies like our own Milky Way. Encircling the grand spiral of the Andromeda galaxy, many smaller galaxies quietly orbit, moving in a complex dance that unfolds over millions, even billions of years. These satellite galaxies, very different in size, shape, and history, are not just bystanders. They are part of a slow, fascinating dance of gravity, motion, and cosmic change. The area around Andromeda is anything but simple. It is a busy neighbourhood, a tiny universe of its own, where interactions and changes constantly reshape the space. The sizes and shapes of these companion galaxies are amazingly varied. Some are compact, smooth, and almost featureless, like the tightly packed elliptical dwarfs. These galaxies with dense centres full of old stars seem to carry the wisdom of the universe in their quiet light. Others are more chaotic, irregularly shaped, and often look like they are in a violent struggle, their forms twisted and pulled as gravity slowly tears them apart. These irregular satellites, often full of gas and areas where new stars form, show the universe's ongoing cycle of creation and destruction. They are living laboratories where stars continue to form, where star nurseries shine like jewels in clouds of cosmic dust, showing that even on the edge of a galaxy, stellar life can grow. Among this group of galaxies, two stand out, M32 and M110. These two companions stay relatively close to Andromeda's bright, busy centre, making them easier to see even with small telescopes used by amateur astronomers. ME32 is a compact elliptical galaxy, almost perfectly round, with stars packed tightly into a very small space. It is like a concentrated jewel of light, where the starlight is thick and bright, giving a sense of closeness. ME110, on the other hand, is bigger and more spread out, its stars stretched over a wider area, giving it a softer, dreamlike look, but even with its gentle appearance, it shows signs of past encounters with Andromeda. Astronomers studying M110 have found signs of old interactions, small ripples in its star distribution, hints of gas that was pulled away, and faint streams of stars stretched outward by gravity. These two galaxies are more than companions, they are living records of Andromeda's long, complex history. Both M32 and M110 are believed to be leftovers of once larger galaxies, stripped of their outer layers and gas by Andromeda's strong gravity many billions of years ago, leaving only their dense cores behind. Beyond these bright neighbours lie many fainter, harder-to-see dwarf galaxies. They orbit Andromeda at much greater distances, like tiny lanterns scattered across the dark waters of space. Some of these dwarfs, like NGC 147 and NGC 185, look like small elliptical galaxies. Their stars are old, calm, and mostly inactive. Very few new stars are forming. They are peaceful and timeless, like tiny cosmic libraries keeping secrets from the early universe. Others, like IC10, are still actively forming stars full of youthful energy. Even with Andromeda's strong gravity, IC10 has kept much of its gas, allowing new stars to form, showing that even the smallest galaxies can resist a giant spiral's pull and keep pockets of star-making alive. For many years, astronomers thought these satellite galaxies were scattered randomly around Andromeda, moving in different directions with little order, each following its own path by chance and gravity. But recent observations have shown something more surprising. Many of Andromeda's satellite galaxies are not scattered randomly. Instead, they seem arranged in a huge, thin plane, like beads on an invisible cosmic string. This arrangement is surprising because it goes against expectations from traditional galaxy formation ideas. It suggests a shared origin. Maybe these satellites were born together in a single event, instead of being caught one by one over billions of years. If true, Andromeda's satellite system is not just a random group of galaxies, but an organized formation, showing a new layer of cosmic structure that challenges old ideas about how galaxies grow and change. Some scientists think this flat arrangement may be part of an even larger cosmic pattern. Perhaps Andromeda's satellites are connected to the Milky Way's own dwarf galaxies, forming threads along huge cosmic filaments, long invisible strands of dark matter and gas that stretch between galaxy clusters. These filaments act like bridges, guiding galaxies along their paths and controlling interactions over huge distances. In this way, the satellite galaxies are not lone wanderers, but part of an interconnected cosmic network, linked to each other and their host galaxies by the unseen force of dark matter. Still, the relationship between Andromeda and its companions is not one way. While Andromeda's gravity is the strongest, it is not completely unaffected by its satellites. The combined pull of these smaller galaxies gently tugs at Andromeda's outer parts, causing its vast disk to bend over time. Though this effect is small and happens over millions of years, it contributes to Andromeda's ongoing change, showing that even small companions can leave a mark on a giant galaxy. In some cases, the interactions are violent. Some of these satellites are slowly being eaten, their stars and gas stretched into long streams as they spiral toward Andromeda's center. Observations have shown huge arcs of stars and gas reaching far into space, leftovers from galaxies already torn apart by gravity. These streams are not just debris, they are living proof of how the galaxy grows through mergers, a process still happening today. One of the most striking examples of Andromeda's eating is the giant stellar stream, a huge ribbon of stars stretching more than 100,000 light-years. This stream is thought to be the remains of a dwarf galaxy that got too close to Andromeda and was slowly pulled apart. Its stars, once part of another galaxy, now mix with Andromeda's halo, becoming part of the larger galaxy. The stellar stream gives an amazing view of cosmic change, a galaxy swallowing its smaller neighbours, taking not just their stars but their histories and weaving them into its own story. Such mergers are not rare. They are part of a continuous cycle of cosmic recycling, showing the restless and dynamic nature of galaxies. Even as some small galaxies are pulled in, others stay surprisingly independent. Some are made almost entirely of dark matter, invisible to normal telescopes but detectable through gravity. These dark galaxies have very few stars and almost no gas, making them nearly invisible in space. Still, they have enough mass to affect nearby objects and reveal the hidden structure of Andromeda's dark matter halo. The existence of these hidden satellites raises big questions about how galaxies form and what dark matter is. How many such hidden galaxies are out there, and what role do they play in shaping the galaxies we can see? Over time, the fates of Andromeda's satellites will keep changing. Some will eventually merge with their host, their stars joining Andromeda's huge stellar population. Others may be thrown into intergalactic space, pushed out by complex gravity or violent encounters. Meanwhile, Andromeda itself is slowly moving toward the Milky Way, on a collision course that will happen in the far future, several billion years from now. This coming meeting will reshape not just Andromeda's satellites but the whole local galactic neighbourhood. The gravitational dance will become stronger, mergers will speed up, and new streams of stars will be pulled into even more complex patterns, continuing the grand story of cosmic evolution. As astronomers study these interactions, each discovery increases our sense of wonder. Andromeda's satellites are not fixed points of light, they are active worlds, each with its own history, each adding to the growth and change of a galactic giant. From the bright compact M32 to the spread-out story-filled M110, from the star-forming IC10 to the calm ancient dwarfs like NGC 147 and NGC 185, each satellite tells a story of survival, struggle, and adaptation under Andromeda's strong gravity. Together, they form a complex, interwoven pattern, showing the hidden rhythms of galaxy life, a tiny universe playing out on the larger scales. By following the motions, shapes, and interactions of these satellites, astronomers learn not only about Andromeda's past, but also about the invisible forces shaping all galaxies. Each orbit mapped, each tidal stream seen, is a clue to the spread of dark matter, the forces shaping the cosmos, and the ways galaxies form. In this way, Andromeda's satellites are more than companions. They are guides, helping us understand the big cosmic puzzle and showing that the universe is more connected and active than we once thought. When a huge star reaches the very end of its life, the universe gets ready for one of its most amazing fireworks shows. This event is called a supernova. To human eyes, a supernova might look like just another distant sparkle in the night sky, but really, it is one of the most powerful and life-changing forces in space. Supernovas are not just the quiet dying of a star, they are violent, dramatic, and world-changing explosions that shake entire galaxies. There are two main ways a supernova can happen. The first way happens when a single giant star, one many times bigger than our Sun, runs out of its natural fuel. A star survives by balancing two opposite forces, the inward pull of gravity and the outward push of energy made in its core through nuclear fusion. For millions or even billions of years, this balance stays steady. But when the star uses up its fuel, gravity wins. The star collapses inward at amazing speed, and this sudden collapse causes a violent explosion that blasts the star's outer layers into space. The second way a supernova can happen involves not one star, but two. In some binary systems, where two stars orbit each other like dance partners, a smaller but very dense star called a white dwarf may quietly sit next to a bigger partner. A white dwarf is already the burned-out core of a dead star, but in a binary system it can still pull in material from its partner. As this stolen material piles onto the white dwarf, the star becomes very unstable. If the white dwarf takes in too much, it cannot hold itself together. Then, it explodes in a runaway thermonuclear blast, tearing itself apart completely. No matter how it happens, the result is the same. The star explodes with almost unbelievable power. In just a few moments, a supernova can release more energy than our Sun will give off in its entire life. This huge blast sends shockwaves outward in every direction. Along with the energy, the explosion throws out newly formed heavy elements, things like iron, calcium, nickel, and gold, into space. These elements are needed to build planets, form atmospheres, and even for the chemistry of life. In a very real way, every person on Earth carries in their bones and blood the old ashes of stars that exploded long before our world existed. Supernovas are not only dramatic ends to a star's life, they are also beginnings. The shock waves from these explosions spread through nearby space. When these waves hit nearby clouds of gas and dust, they squeeze them. Sometimes, this squeezing starts the birth of new stars. In this way, the death of one star can spark the creation of many others. Without the cycle of stars dying and new ones forming through supernovas, galaxies like Andromeda and our Milky Way would be empty, without the materials needed for rocky planets, oceans, forests, and living things. The Andromeda galaxy, the closest big galaxy to our Milky Way, has its own dramatic history of supernovas. These events shaped its stars, shaped its nebulae, and added to its chemical makeup. When we look at Andromeda today, a huge spiral of hundreds of billions of stars, we are not just seeing quiet, steady light. We are seeing the results of countless explosions over millions of years, explosions that built the galaxy's very structure. One of the most famous and studied supernovas in Andromeda happened in 1885. This event, called SN 1885A, was seen from Earth and left behind a remnant that still interests astronomers. Unlike many supernova remnants that fade away over time, this one is still a main subject of study because of its location and special features. SN 1885A was a Type Ia supernova, meaning it came from a white dwarf in a binary system taking in too much material and exploding. What makes this supernova very interesting is that it happened very close to Andromeda's center. When it blew up, it spread iron and other heavy elements into the surrounding space. Even today, astronomers using modern telescopes can see faint signs of this explosion, like a ghostly shadow in the heart of the galaxy. This event also helped astronomers prove something very important. Andromeda is not very different from our Milky Way in having such huge explosions. In both galaxies, stars can live, die, and explode in the same ways. By studying SN 1885A and others like it, scientists learned that supernovas are universal events that help shape galaxies across space. But Andromeda is not home to just one or two famous explosions. Across its sweeping spiral arms and thick central areas, there is a huge network of supernova remnants, glowing shells of gas and energy left after a star's violent death. Some of these remnants are fairly young, only a few thousand years old. To humans, 1,000 years might seem extremely long, but for galaxies it is just a blink. These young remnants still shine brightly in X-ray and radio light, their shock waves still changing the space around them. Their expanding shells look like glowing bubbles of gas, slowly stretching outward into the dark. Others are very old, maybe tens or hundreds of thousands of years old. Over time, their shells fade and their energy spreads out. Eventually, their shapes blend into the wider space filled with gas and dust that makes up the galaxy. But even when their shapes are gone, their effects remain. The heavy elements they threw out continue to float through the galaxy, helping form future stars and planets. By studying these remnants, astronomers can trace Andromeda's past. They can see where massive stars once lived, which areas of the galaxy had lots of star formation, and how these events changed the galaxy's chemical makeup. Many remnants are along Andromeda's spiral arms, the same places where new stars are still forming. This makes sense because massive stars that become supernovas usually form in dense star-forming areas, but some remnants are in surprising places, in quiet areas where stars are not forming much today. These unexpected spots show that Andromeda had bursts of star formation in the past, events that have since slowed but left their marks. The role of supernovas in shaping Andromeda cannot be overstated. The shock waves they create act like galaxy sculptors. Imagine a ripple spreading across a pond after a stone is thrown in. Now make that ripple hundreds of light years wide. These ripples stir up gas clouds, triggering collapses that form new stars. Without them, Andromeda's spiral arms would not shine so brightly and many of its stars might never have formed. Beyond star formation, supernovas also make heavy elements. Lighter elements like hydrogen and helium were made in the Big Bang, but heavier elements, needed for complex chemistry, are made in stars and released in supernovas. Without supernovas, there would be no iron for blood, no calcium for bones, no oxygen for lungs, and no carbon for life. In short, supernovas are the makers of life's essential ingredients. Not all supernova remnants in Andromeda are the same. Some are very powerful, shining brighter, or releasing more energy than expected. In some cases, these remnants are linked to neutron stars, the collapsed cores of massive stars that survived the explosion. Neutron stars are extremely dense, packing more mass than our Sun into a ball only about 20 kilometers wide. Some of these neutron stars spin fast and emit beams of radiation like cosmic lighthouses. Astronomers call them pulsars. These pulsars keep shining long after the supernova has faded, acting as beacons that can be seen across huge distances. By studying pulsars in Andromeda, astronomers learn about extreme matter, how gravity works in intense conditions, and the role of these unusual objects in shaping galaxies. The influence of supernovas does not stop with their remnants. The spreading shock waves speed up cosmic rays, particles moving through space nearly at the speed of the light. These high-energy particles move through Andromeda, heating gas, changing its chemistry, and even ionizing hydrogen clouds. Cosmic rays affect how new stars form, how gas clouds change, and how energy moves through the galaxy. Some supernova remnants in Andromeda also suggest a more complicated past. If certain remnants are in unusual places or show unusual traits, it could mean Andromeda swallowed smaller galaxies in the past. These dwarf galaxies, pulled apart by Andromeda's gravity, may have had massive stars that later exploded as supernovas. In this way, some of the oldest remnants we see today may not have started in Andromeda, but in galaxies it absorbed long ago. Looking at the bigger picture, the story of supernovas in Andromeda is also the story of life itself. Without the cycle of stars exploding, spreading elements, and triggering new stars, there would be no Earth and no people. The iron in your blood, the oxygen in your breath, the calcium in your bones, all of these were made in stars that lived and died billions of years ago. The discovery of planets beyond our own solar system is one of the most amazing and mind-opening achievements in modern astronomy. For centuries, people looked up at the night sky and wondered if other worlds orbited distant stars, if somewhere out there in the huge universe there might be planets like Earth, maybe even with life of their own. For a long time, these questions could not be answered. Telescopes were strong enough to show us galaxies, nebulae, and the fiery details of stars, but planets around those distant suns remained hidden. That began to change only in the last years of the 20th century. By 1992, astronomers announced the discovery of the first confirmed exoplanets, planets orbiting stars beyond our Sun. Since then, progress has been amazing. In just a few decades, scientists have confirmed thousands of exoplanets in our own Milky Way galaxy, with thousands more waiting to be confirmed. Some are huge gas giants bigger than Jupiter, others are rocky worlds more like Earth, and some are strange types of planets that we never imagined before. Yet, as incredible as this wave of discovery has been, a bigger challenge is ahead: finding planets beyond our own galaxy. The idea of finding exoplanets in the Andromeda galaxy, or even further away, seems almost like science fiction. And yet, astronomers are starting to take their first real steps toward making it possible. Before we look at how we might find planets in another galaxy like Andromeda, it helps to understand how we already find them in our own Milky Way. Over the years, scientists have developed a few clever ways to detect planets orbiting distant stars. The most successful way so far is called the transit method. This works like a cosmic shadow play. Imagine a small planet orbiting its star. From our view, if that planet happens to pass directly in front of its star, it blocks a tiny bit of the star's light. The star dims slightly, then brightens again once the planet moves past. By carefully watching for these repeating dips in brightness, astronomers can tell not only that a planet is there, but also how big it is and how long it takes to orbit its star. NASA's Kepler Space Telescope and its successor, TESS, use this method to discover most of the known exoplanets. Another important method is the radial velocity method. This one doesn't rely on seeing a planet's shadow, but on noticing its gravitational pull. A planet, Even a small one pulls on its star as it orbits, making the star wobble slightly. By measuring the star's light and how its spectrum shifts back and forth, astronomers can detect that wobble and figure out that a planet is there. This method has been especially useful for finding large planets close to their stars. Other methods exist too, like taking direct pictures of a planet, which is rare but possible for giant worlds far from their stars, or detecting planets by how they affect pulsars, spinning dead stars that emit regular beams of light. But for most discoveries, the transit and radial velocity methods remain the main tools. These methods work very well for stars that are relatively close to us in the Milky Way. But the farther a star is, the harder it becomes. Detecting a tiny dip in brightness, or a tiny wobble in motion, requires extreme precision, and when the stars are millions of light years away, those signals are too faint for our current tools. This is why the challenge of finding planets in the Andromeda galaxy is so huge. Andromeda, also called M31, is the nearest large spiral galaxy to us. Yet it is still unimaginably far, about 2.5 million light-years away. To understand that, if you could somehow travel at the speed of light, it would take 2.5 million years to reach Andromeda. For comparison, modern humans have only existed for about 300,000 years. Andromeda is enormous. It contains well over 1 trillion stars, several times more than the Milky Way. With so many stars, it almost certainly contains even more planets. Some might be rocky and Earth-like, some might be gas giants like Jupiter, some might be icy worlds frozen in eternal winter, and others might be so strange that we cannot yet imagine them. But how can we hope to find them from so far away? Here is where a remarkable method called gravitational microlensing comes in. This method uses a trick of gravity itself, as explained by Albert Einstein's theory of general relativity. Gravity does not just pull on matter, it bends light. If a massive object like a star passes directly in front of a more distant star, its gravity can act like a lens, bending and magnifying the light from the background star. The background star appears to brighten for a short time, and then fade back to normal. This is called a microlensing event. Now, here is the clever part. If that foreground star has a planet orbiting it, the planet's gravity can create a second, smaller brightening in the light. In this way, astronomers can detect a planet, even if they cannot see the star itself clearly. Unlike the transit or radial velocity methods, microlensing does not require us to see individual stars in distant galaxies. Instead, it lets us spot planets indirectly through their gravitational effects. This method has already been used successfully in the Milky Way to find planets that would otherwise be invisible. And in 2020, astronomers reported something extraordinary: the possible detection of a planet in another galaxy, the Whirlpool Galaxy, about 23 million light-years away. Using X-ray observations, they noticed subtle changes in the emissions from a binary system, which could only be explained if a planet were there. Although this detection is not confirmed, it was the first hint that planets outside our galaxy might really exist, and could one day be found in larger numbers. Andromeda, with its dense and crowded core full of overlapping stars, is the perfect target for microlensing. In theory, if astronomers watch Andromeda long enough, they should see microlensing events that reveal planets orbiting its stars. Each event might last only hours or days, so patient and consistent observation is crucial. Even if we succeed in detecting planets in Andromeda, what we can know about them will be limited. In the Milky Way, when a new exoplanet is discovered, astronomers often follow up with more observations to estimate its size, mass, and sometimes even clues about its atmosphere. Using space telescopes like Hubble or the James Webb Space Telescope, scientists can analyze starlight as it passes through a planet's atmosphere, revealing gases like hydrogen, helium, carbon dioxide, or even water vapor. But with Andromeda, the distance makes such follow-up impossible. For now, we will only be able to detect that planets exist, not their details. We may not know if they are rocky or gaseous, if they have thick atmospheres, or if they could support life. Still, knowing that planets exist in another galaxy would itself be one of the most important discoveries in science. In the Milky Way, astronomers often talk about the habitable zone, the region around a star where conditions might allow liquid water to exist on a planet's surface. Water, as far as we know, is essential for life. Many of the exoplanets discovered so far orbit within the habitable zones of their stars, raising the exciting possibility that they could support life. Applying this idea to Andromeda is much harder. Even if we detect a planet in Andromeda and calculate that it lies in its star's habitable zone, confirming whether it actually has water or an atmosphere is beyond our abilities right now. And yet, given the similarities between Andromeda and the Milky Way, it seems reasonable to assume that some planets there resemble Earth in important ways. Some may have oceans, continents, and thick cloudy atmospheres. Others may be frozen wastelands or burning deserts. There may even be worlds with conditions completely different from us. Planets covered in strange ices or orbiting dim red stars where life might evolve in ways we cannot imagine. What makes Andromeda especially interesting is its history. Unlike the Milky Way, which has had a relatively calm life, Andromeda has gone through several mergers with smaller galaxies. Over billions of years it has swallowed many neighbours. These cosmic collisions shake up stars and planets, disturbing stable systems. As a result, Andromeda may contain many rogue planets, worlds that were kicked out of their solar systems during these chaotic mergers and now drift freely in space, no longer orbiting a star. These orphaned planets would be extremely hard to detect, but they may be very numerous, hidden in the galaxy's halo far from the bright spiral arms. If planets exist in Andromeda, their environments would depend on where in the galaxy they are. In the core of Andromeda, planets would orbit stars packed tightly together, exposed to strong radiation and gravity. Life there would be unlikely. In the spiral arms, conditions might be more familiar, similar to our own solar neighbourhood in the Milky Way. Here, planets might orbit stars in relative stability, with a mix of gas giants, rocky planets, and icy worlds. In areas full of supernova leftovers and star clusters, planetary formation might be disturbed, leading to unusual systems. Near black holes scattered through the galaxy, planets might face extreme gravity challenges. Searching for exoplanets, especially in distant galaxies, produces huge amounts of data. Looking through this data for faint signals is a job well suited to artificial intelligence. Already, machine learning programs are being used to reanalyze old data from Kepler and TIAS, finding planets that humans missed. As these tools improve, they may become essential for detecting subtle microlensing signals from galaxies like Andromeda. Of course, finding planets in Andromeda immediately raises a tempting question. Could we ever travel there? The idea of intergalactic travel is one of the most ambitious and speculative dreams in physics. The challenges are enormous. Andromeda is about 2.5 million light-years away. Even if we could build a spacecraft that travels at the speed of light, which current physics says is impossible, it would still take 2.5 million years to get there. The fastest spacecraft ever built by humans, NASA's Parker Solar Probe, travels at about 430,000 miles per hour. At that speed, a trip to Andromeda would take more than 4,000 times the entire span of human history. Clearly, chemical rockets and current engines cannot take us beyond the Milky Way. Scientists are exploring bold new ideas. Light sails powered by giant lasers could, in theory, push spacecraft to a large fraction of the speed of light. The Breakthrough Starshot project is already testing this idea on a small scale, aiming to send tiny probes to Alpha Centauri, our nearest star system, within a human lifetime. Scaling this up for intergalactic travel would be extremely hard, but it is not completely outside the rules of physics. Antimatter propulsion is another idea. Antimatter gives off huge amounts of energy when it meets normal matter. If we could make and store it safely, it might one day power spacecraft to near-light speeds. Nuclear fusion engines, powering spacecraft the way stars power themselves, could provide long-lasting, efficient push. These ideas are still just ideas, but they keep the dream alive that one day, maybe far in the future, humans might leave the Milky Way and travel to galaxies like Andromeda. Antimatter is perhaps the most amazing and powerful substance that modern science has ever thought of. Unlike normal matter, which makes up everything we see around us, antimatter can release unbelievable amounts of energy when it meets its opposite, regular matter. When the two touch, they destroy each other completely, leaving behind nothing but pure energy. This makes antimatter the most energy-packed material ever known, much more powerful than the fuels we use in rockets today. To understand how powerful it is, even a very small amount of antimatter, just a few grams, could release more energy than thousands of tons of chemical fuel. This is why many scientists and engineers dream of one day building spacecraft powered by carefully controlled antimatter reactions. Such a ship could travel at speeds far greater than anything chemical rockets could ever reach. With our current rockets, which rely on burning fuel, we can only reach a small fraction of the speed of light. But with antimatter, the dream of travelling across the stars starts to seem more possible. Of course, there is a big problem. Making and storing antimatter is something we cannot yet do on a useful scale. In modern labs, scientists have managed to make only a few atoms of antimatter at a time, and even then, keeping it stable is almost impossible. The tiniest contact with matter destroys it instantly, releasing dangerous amounts of energy. For now, antimatter-powered spacecraft remain an exciting idea on paper, waiting for new discoveries in both physics and engineering. But let us imagine, just for a moment, that humans overcome these problems. Suppose we manage to build a spacecraft capable of reaching speeds close to the speed of light. Something amazing happens when objects move at such incredible speeds. Time itself starts to act differently. According to Einstein's theory of relativity, travelers on a near-light-speed ship would experience time passing much more slowly than people who stay on Earth. This strange effect is called time dilation. For example, while the trip to the Andromeda galaxy might take millions of years when measured from Earth, those on the ship could experience the journey as lasting only a few decades. In their own experience, the impossible distance becomes manageable. Yet, antimatter propulsion is not the only idea dreamers and scientists have thought of. Some have wondered if we might use the power of nature's most extreme objects, black holes. A black hole is so huge and dense that not even light can escape from it. Some ideas suggest that black holes could be used as energy sources, as gravity slingshots, or maybe in ways we cannot yet imagine, to help push ships across space. Another bold idea is the Alcubierre warp drive, a theoretical solution to Einstein's equations. Instead of pushing a spacecraft through space at extreme speeds, the warp drive would bend space itself. Space in front of the ship would shrink, while space behind it would stretch, effectively moving the ship forward without the ship itself breaking the universal speed limit of light. From the outside, it would look like the ship was travelling faster than light, but actually, it would be space itself that moves. However, such a drive would need types of energy that we have never seen in the real universe, things like negative mass or exotic energy. These are not materials we know how to make, and they might not even exist. For now, the warp drive stays a fascinating mathematical idea, more like science fiction than engineering plans. Beyond these human-made ideas, there is also the chance that nature has already provided shortcuts across the universe. One of the most famous possibilities is the wormhole. A wormhole, if it exists, would be like a tunnel through space and time, connecting two faraway points. Imagine folding a sheet of paper so that two faraway points touch. A wormhole would act like the shortcut through the fold. With such a bridge, a spacecraft could skip the unimaginably huge distances between galaxies in an instant. The problem, however, is that no one has ever found proof that wormholes exist, and even if they do, keeping one stable and open long enough for a ship to go through would probably need exotic matter, with properties unknown to physics. Still, many scientists think that if advanced civilizations exist somewhere in the universe, they might have already figured out such technologies. Even if we figure out how to travel faster or take shortcuts, there is still another problem: survival. A trip across galaxies is not like a road trip across countries. We're talking about thousands, maybe even millions of years of travel. How could humans survive such long journeys? One solution might be to keep life going aboard the ship for many generations, with children, grandchildren, and their descendants continuing the mission. Another possibility is far more futuristic: putting travelers into suspended animation. This idea comes from nature. Some animals, like bears, go into hibernation, slowing down their bodies for months at a time. Scientists are studying whether humans could one day be put into similar deep sleep states for space journeys. Another approach is cryogenic freezing, keeping the body at extremely low temperatures and waking it later. But the biological challenges of freezing and safely bringing a human back to life are huge and remain unsolved. There is also a more extreme alternative. Maybe we should not send humans at all. Instead, we could send machines. One especially interesting idea is self-replicating robotic probes. This idea was first suggested by the mathematician John von Neumann. He imagined spacecraft that would carry advanced artificial intelligence and could build copies of themselves. When such a probe reached a new star system, it could use local resources, make another probe, and send it further. Over time, these machines could spread across the whole universe, carrying information and exploring galaxies without the risks and difficulties of human travel. The beauty of this idea is that, once launched, the system would keep going on its own. The probes could keep traveling forever, maybe for billions of years, spreading human knowledge and presence far beyond what human bodies could handle. Some scientists even guess that if intelligent civilizations exist elsewhere, their first contact with us might not be through living beings but through such probes. For now, all these possibilities, antimatter rockets, warp drives, wormholes, hibernation chambers, and robotic explorers, are still just ideas and imagination. But history has shown us that human technology grows in leaps we often cannot predict. Ideas that once seemed impossible, flying in the sky, speaking across the world instantly, or walking on the moon, are now part of everyday life. Maybe one day the dream of travelling to faraway galaxies will change from fantasy to reality. The Andromeda Galaxy is one of the biggest and most fascinating objects in our night sky. It is the closest large spiral galaxy to our own Milky Way, and for centuries it has caught the attention of stargazers, storytellers, and scientists. At first look, especially when seen through simple telescopes or even with the naked eye from very dark places on Earth, Andromeda looks like a faint misty cloud stretched across the sky. But what the human eye can see is only a tiny part of the galaxy's true form. Much of Andromeda's amazing detail remains hidden, covered by huge clouds of space dust. This dust is not like the dust in our homes, but tiny grains of carbon, minerals, and ice scattered through space. These space particles absorb and scatter visible light, the same light our eyes can see. Because of this, large parts of Andromeda's structure disappear behind this dusty cover, leaving astronomers with only pieces of the full picture. Trying to study Andromeda using only visible light is like trying to look through a smoky window. You might see bits of what's beyond, but the full view stays hidden. Infrared light, however, changes everything. Unlike visible light, infrared can pass through much of the dust. This lets astronomers look past the dark curtains that block our view and see Andromeda in a whole new way. Using infrared telescopes, both in space like the Spitzer Space Telescope and on the ground with infrared detectors, scientists have found amazing details about Andromeda's structure, history, and ongoing activity. These discoveries have not only deepened our understanding of this nearby galaxy, but also helped us learn more about how galaxies form, grow, and interact. One of the most striking discoveries infrared light has shown is the detailed shape of Andromeda's dust lanes. In normal visible images, these dust lanes look like dark streaks weaving through the galaxy's spiral arms. They appear like dark scars across the glowing starry disk, blocking the light of millions of stars behind them. But when astronomers look in infrared, these same lanes change dramatically. Instead of appearing dark, they start to glow with a faint but steady warmth. Infrared detectors can sense the energy given off by dust particles that have absorbed starlight and then released it at longer wavelengths. In this view, what was once invisible becomes visible. What was only a dark patch now shows itself as a detailed network, a framework that traces the hidden shape of the galaxy. This dust is more than just a problem for astronomers. It is a key part of how stars are made. Dust, together with clouds of hydrogen gas, forms the raw material for new stars. In areas where the dust and gas get especially dense, gravity pulls matter together. Over millions of years, this can cause a gas cloud to collapse, eventually forming new stars. By mapping these cold dust clouds in infrared, astronomers can figure out where the next generations of stars in Andromeda will appear, long before they shine in visible light. It's almost as if infrared astronomy gives us the power to see the future, showing the birthplaces of stars before they awaken and shine brightly in the night. If the spiral arms of Andromeda are like grand pathways winding through the galaxy, then its center is the beating heart. The middle of Andromeda is packed with stars, so many that in visible light they blend into a single bright glow. This makes it very hard for normal telescopes to see the fine details of the core. Once again, infrared light offers a solution. By cutting through the brightness, infrared telescopes can reveal the hidden structures and motions at the very center of the galaxy. At the heart of Andromeda lies a supermassive black hole, one with a mass equal to millions of suns. Around this black hole is a dense spinning disk of stars, In visible light, this area often looks like a featureless bright blob, but in infrared, astronomers can see the complex movements of stars as they orbit the black hole's strong gravity. They can watch entire star systems move around this invisible giant, giving key clues about how the galaxy's center works and its history. This ability to cut through the glare has given scientists a close look at a galaxy's center, helping them study how supermassive black holes grow, how they affect the stars around them, and how these central regions change over billions of years. Not all stars shine the same way. As stars get older, they go through big changes, many of which make them stand out more in infrared light. Red giant stars in particular are bright in infrared. These stars have used up the hydrogen in their cores and expanded to huge sizes, glowing with a cooler but stronger light that is most visible in longer wavelengths. By mapping these red giants, astronomers can trace the long history of Andromeda. These older stars act like fossils, keeping the memory of events that shaped the galaxy over time. For example, if a part of Andromeda has a lot of red giants, it likely had a burst of star formation billions of years ago. Areas with fewer of these old stars might be younger, still filled with middle-aged stars. Infrared studies of Andromeda have let astronomers build a timeline of its growth, showing where ancient stars settled and how the galaxy slowly matured. Through these observations, Andromeda stops being just a flat image in the sky and becomes a living history book written in starlight. Galaxies are not alone in space. They often interact, collide, and merge. When this happens, they leave behind subtle traces, tidal tails, streams of stars, and wide, faint arcs of dust and stars stretching across space. Seeing these features in visible light is very hard because they are faint and spread over huge distances. Infrared surveys, however, are very good at picking up the warm glow of dust and the faint light of stars left behind by these events. In Andromeda, astronomers have found multiple stellar streams, ghostly remains of smaller galaxies torn apart by Andromeda's strong gravity long ago. These streams are the scars of ancient galaxy-eating events, each one telling the story of a smaller system swallowed by Andromeda. By following these features in infrared, astronomers can piece together Andromeda's past encounters. They can tell when and where dwarf galaxies merged into its structure, reshaping its spiral arms and adding new material for star formation. These faint signs of cosmic collisions show that galaxies, like living things, grow and change by consuming smaller neighbours. One of the most surprising benefits of infrared observations is their ability to detect small objects that are almost invisible in normal light. Among these are brown dwarfs, sometimes called failed stars. Brown dwarfs form like regular stars collapsing from clouds of gas and dust. But unlike true stars, they never get big enough to start lasting nuclear fusion in their cores. This means they cannot shine like stars such as the Sun. Instead, they give off most of their weak light in the infrared, glowing gently with leftover heat from their formation. Because they are so dim in visible light, brown dwarfs were almost completely hidden until infrared technology improved. Now, thanks to advanced infrared surveys, scientists have found groups of brown dwarfs spread throughout Andromeda. These discoveries are filling in the missing parts of our understanding of the galaxy's stars. Brown dwarfs may not shine like real stars, but they are still important. They represent the smallest type of cosmic object, bridging the gap between stars and giant planets. By studying them, astronomers learn about all the processes that control star and planet formation. In Andromeda, finding these faint companions shows how diverse the galaxy really is. Infrared astronomy has given us the power to look past the dust, brightness, and hidden objects that once limited our understanding of galaxies like Andromeda. Through this new vision, astronomers have revealed the glowing dust lanes, the star-making nurseries of the future, the hidden movements of stars around a central black hole, the fossil record of old stars, the faint scars of past mergers, and the hidden population of brown dwarfs. In a way, to see Andromeda in infrared is to see it as it really is. It is to see not just the glittering light of stars, but also the deeper workings that drive the galaxy's growth. Each infrared image adds another chapter to the story of Andromeda, one of creation, change, and cosmic memory. When we look at the great Andromeda galaxy with our eyes or with regular telescopes that see visible light, we see a beautiful spiral of stars wrapped in lanes of dust. When we use infrared light, we can see through some of that dust and spot hidden stars, glowing clouds, and the warmth of cosmic structures. But when astronomers listen to the sky with tools that pick up radio waves, a very different view of Andromeda appears. Radio astronomy does not show twinkling stars or glowing dust. Instead, it shows a picture shaped by invisible magnetic forces, by cold, ghostly clouds of gas, and by faint, almost secret signals of cosmic events that have been travelling through space for millions of years. This radio view is strange and unfamiliar, but very important because it shows parts of the galaxy that cannot be seen in any other way. One of the main tools of radio astronomy in studying Andromeda is mapping hydrogen gas. Hydrogen, the most common element in the universe, is usually invisible to normal telescopes. But when hydrogen is neutral, meaning its atoms are not charged, it gives off a very faint radio signal. This signal has a specific wavelength of 21 centimeters, so precise that it is often called the hydrogen line. By tuning their radio instruments to this wavelength, astronomers can trace where hydrogen gas is in the galaxy. It is like tuning a radio to the right station, but instead of music, what comes through is the soft, steady signal of hydrogen atoms across space. By collecting this signal from many points in Andromeda, researchers can make detailed maps of its gas structure. These maps show not only where hydrogen is, but also where new stars might form, since dense hydrogen clouds often collapse to make stars. They also show how Andromeda's spiral arms are shaped and how they continue to grow and twist over time. These hydrogen maps have revealed something amazing. Andromeda's disk is much bigger than it looks in normal images. With visible light, the bright part of the galaxy seems to stretch about 220,000 light-years across. But radio maps, which show hydrogen gas, reveal that Andromeda's gas disk goes even farther, fading slowly into the thin matter between galaxies. This means Andromeda is even larger and more spread out than we could guess with our eyes. Visible light shows the shapes of stars. Infrared light shows the warmth of dust. But radio waves show something more hidden, the effect of magnetic fields. The universe is full of charged particles, tiny pieces of matter like electrons and protons, moving at incredible speeds. When these particles spiral around magnetic field lines, they produce a faint type of radio signal called synchrotron radiation. It is not bright or flashy, but it is steady and reliable. By detecting and mapping this radiation, astronomers have found that Andromeda has a surprisingly organized magnetic field that stretches across much of the galaxy. This magnetic field is not just interesting, it plays an active role in shaping Andromeda. It guides the paths of cosmic rays, mysterious high-energy particles that streak across space. It also affects how interstellar gas moves, clumps, and sometimes collapses into stars. In this way, the invisible magnetic field quietly shapes star formation, sculpting the future of the galaxy in ways that visible light cannot show. Another wonder seen with radio astronomy is the presence of pulsars in Andromeda. Pulsars are the rapidly spinning remains of massive stars that exploded as supernovas. What is left is a neutron star, a city-sized sphere so dense that a teaspoon of its material would weigh more than mountains. As these neutron stars spin, they send out powerful beams of energy, like the beams of a cosmic lighthouse. Each time the beam sweeps past Earth, our telescopes detect a pulse of radio waves. That is why they are called pulsars. Andromeda is millions of light-years away, yet its pulses can still be detected across space. Sensitive radio telescopes on Earth have found several of these rhythmic beacons in our neighbouring galaxy. Each pulse is a heartbeat from a long-dead star, carrying a message across time about the last stages of a star's life in another galaxy. At the centre of Andromeda is a supermassive black hole. Astronomers call it M31, though it is not as active as the giant black holes at the centres of galaxies like quasars. Still, Andromeda's central black hole gives off faint radio signals. These signals come from charged particles trapped in the strong magnetic fields near the black hole. Spiraling almost at the speed of light, these particles release energy that radio telescopes can detect. By studying this glow, astronomers can look into the busy heart of Andromeda and learn about how its black hole feeds. Sometimes it swallows matter greedily, sometimes it starves, and these patterns show up in the radio signals that spread out into space. Andromeda holds more secrets than astronomers have solved. Beyond the central black hole, radio telescopes have found strange radio sources scattered across the galaxy. Many of these sources do not match anything seen in visible or infrared images. Some may be echoes of ancient supernovas, star explosions that blasted gas outward, making it glow in radio waves. Others may be star nurseries, places where young massive stars pour energy into their surroundings, ionizing the gas and creating radio bursts. But not all sources are easy to explain. Some remain mysterious, flickering on radio maps with no clear cause. Studying them is an ongoing challenge, needing more sensitive tools and careful observation. Radio astronomy is also used to ask one of humanity's boldest questions: are we alone? Radio waves can travel huge distances without being blocked or scattered, so they are a good way to communicate across space. Humans use radio signals for music and to talk to spacecraft far away. It is reasonable to think that if intelligent life exists elsewhere, they might also use radio waves to communicate. With this in mind, astronomers have pointed radio telescopes at Andromeda, hoping to find a pattern in the static, something structured, intentional, and different from random noise. So far, no such signal has been found. But the search goes on as part of SETI, the search for extraterrestrial intelligence. The idea that beings in another galaxy might one day call across space is too fascinating to ignore. The future of radio astronomy promises even more discoveries. A giant new telescope called the Square Kilometre Array is being built. As its name shows, its total collecting area will cover 1 square kilometre, making it the most powerful radio telescope ever. When finished, it will let astronomers map Andromeda's magnetic field in much greater detail. It will be sensitive enough to detect the faintest hydrogen signals, showing the finest threads of gas that feed the galaxy. It will also find hidden sources of radio waves that today remain invisible. Through radio astronomy, Andromeda reveals itself not just in light, but in quiet signals. Its hydrogen gas hums gently at 21 centimeters. Its magnetic fields glow with faint synchrotron radiation. Its pulsars beat like cosmic drums. Its black hole murmurs with trapped particles. Even its mysterious radio sources add to the cosmic chorus. When scientists talk about the conditions needed for life, they usually start with the same set of rules no matter where in the universe they are looking. These are the basics of what we call habitability. First, a planet needs a steady orbit around its star. If the orbit is too unstable, the planet might swing wildly closer or farther from the star, causing extreme changes in temperature that would make life nearly impossible. Second, that planet must lie within a special area called the habitable zone. This is the sweet spot around a star where temperatures are just right for liquid water to exist. Water is considered essential because on Earth, every form of life depends on it. Third, a planet needs to keep an atmosphere, one thick enough to protect it and rich enough in chemicals to support the building blocks of life. When astronomers study planets inside our own Milky Way, these rules are fairly well understood. We have found many exoplanets, and we can measure whether they meet some of these conditions. But when these same ideas are applied to the Andromeda galaxy, things become much more complicated. Andromeda is over 2 million light-years away, far beyond the reach of our current telescopes to study individual planets directly. Instead of looking at those planets directly, scientists must take a broader approach. They study Andromeda's stars, its shape, and its history of planet formation. From this, they try to put together an educated guess about where life might have the best chance of existing. One of the most important clues comes from the stars themselves. Planets fit for life cannot form out of just hydrogen and helium, the simplest gases that made up the early universe. They need heavier elements such as carbon, oxygen, and nitrogen, which are important for creating atmospheres, water, and the molecules of life. These heavier elements, what astronomers call metals, even if they are not metals in everyday life, are made inside stars and spread through space when those stars die in supernova explosions. In this regard, Andromeda is full of possibilities. It has a mix of both young and old stars. The presence of younger stars shows that planet formation is still happening, much like in the Milky Way. This raises the chances that rocky Earth-like planets have formed within habitable zones around those stars. But Andromeda also shows signs of a violent past. Over billions of years, it has swallowed smaller galaxies through a series of mergers and cosmic crashes. These violent events have shaped its structure, but also put planets and life at risk. Galactic collisions can disturb the orbits of stars, flood areas with harmful radiation, or throw planets out into the cold emptiness of space. Today, much of Andromeda has settled into a mostly stable state, but certain regions, especially near its crowded centre or in areas with very high star density, may still be too chaotic to support long-term stable planetary systems. By contrast, the outer spiral arms of Andromeda may offer safer neighbourhoods. Here, stars and planets could orbit quietly for billions of years, giving life time to develop and grow. In our own Milky Way, we have already found exoplanets that have water, as well as icy moons orbiting gas giants that may hide oceans under thick layers of ice. These frozen moons remind us that life might not be limited to planets within the usual habitable zone. Beneath their icy surfaces, internal heating from tidal forces or radioactive decay can keep underground oceans liquid, offering possible homes for life. If similar moons exist in Andromeda, they too might serve as cradles for life. The difficulty, of course, is that finding such details in Andromeda is much harder than in the Milky Way. At such a huge distance, we cannot yet see individual planets well enough to know whether they have water or atmospheres. For now, it is beyond our technology. Still, scientists allow their imagination to go further. What if life in Andromeda does not even follow the same rules as life on Earth? Some researchers think that in extreme environments, organisms could be based not on carbon, as we are, but on silicon, which has chemical properties that might let it form complex structures. Such life could live in places poisonous to us. Andromeda has every kind of star, from faint red dwarfs to massive blue giants, and the planets around them may face conditions very different from anything we know. Some could have thick atmospheres filled with gases such as ammonia or methane. If so, then life might arise there in strange unfamiliar forms, expanding the possibilities of what we call habitability. In the Milky Way, astronomers looking for life search for biosignatures, chemical signs in exoplanet atmospheres that suggest life. These signs include oxygen, methane, and carbon dioxide, which together can hint at processes that only life can keep going. Finding such signs in Andromeda would be extremely hard with today's instruments, but perhaps in the future, new telescopes will be able to study exoplanet atmospheres even at such huge distances. Scientists could then look for atmospheres that seem off, where the mix of gases could not be explained by geology alone, and would need life to make sense. And what if Andromeda does not just have life, but also civilizations? This is a question that stretches the imagination even more. If an advanced species arose there, it might leave behind signs of its technology. Just as the search for extraterrestrial intelligence, SETI, listens for radio signals in our own galaxy, astronomers could look for artificial signals from Andromeda, radio waves, laser pulses, or even huge energy-harvesting structures like Dyson spheres. Such megastructures, if they existed, would give off infrared radiation that might one day be detectable with strong instruments. But the obstacles are huge. Andromeda is not just far away, it is enormous, containing hundreds of billions of stars. Alien civilizations may use technologies or ways of communication completely unlike anything humans can imagine. If so, their signals might go unnoticed, hidden in plain sight. Another interesting factor is Andromeda's age. It has been forming stars for billions and billions of years, far longer than human history. If intelligent life appeared early in its timeline, it could now be millions of years ahead of us in development. Such a civilization might have powers beyond our understanding, or it might have already disappeared, leaving behind only traces of its existence. If one day humans dare to look beyond the familiar stars of the Milky Way and aim to settle the huge Andromeda galaxy, the challenge would be unlike anything we have ever faced. Such a task would not be a single bold jump, but rather a carefully planned and step-by-step journey. It would need technology far beyond what we now have, a vision that reaches across centuries, and a deep understanding of how life can survive in the silent, harsh ocean of space between stars. To prepare for this, dreamers have imagined what might be called the Andromeda Plan, a big and theoretical guide that would lead humans' expansion beyond their home galaxy. This plan would not be a simple instruction book, but rather a roadmap that lasts for generations, starting with the very first scouting missions and ending only when fully independent colonies thrive in a galaxy millions of light years away. The very first and most important step would be to solve the puzzle of travel itself. Andromeda is not just around the corner, it is more than 2 million light years away. Ordinary rockets, the kind that carried astronauts to the moon, or even robot explorers to the far planets, would be completely useless. Humans would need intergalactic engines, machines that can push ships across distances so huge they are hard to imagine. To do this, big breakthroughs would be needed in technologies that today seem almost like dreams, engines powered by antimatter, or maybe even the famous Alcubierre warp drive, which could in theory bend space itself to make the trip shorter. Before a single human ever leaves the Milky Way for Andromeda, the first wave of explorers would not be people at all, but machines. Robot probes, equipped with powerful artificial intelligence, would take the first step. These would not be the slow and simple probes we have now, which send radio signals that take minutes or hours to reach Earth. Intergalactic probes would have to think and make decisions on their own, acting as scouts in a wilderness so far away that waiting for instructions from Earth would be impossible. Their mission would be to find habitable worlds, measure the dangers of strange stars and black holes, and map out the resources scattered through Andromeda. To send their findings home, they might use communication methods that seem almost like science fiction, maybe even quantum entanglement, which would let information travel instantly across the cosmic gap. Once a suitable place is found, the next stage of the Andromeda plan would begin. Self-replicating robot factories would be sent, carrying the beginnings of industry inside them. Equipped with tiny machines and advanced 3D printing systems, these factories could mine asteroids, gather planetary materials, and build the first structures of a future civilization: space stations, energy collectors, and shelters able to survive harsh alien conditions. Even before humans set foot on a planet, robot terraformers might start changing atmospheres, releasing engineered microbes that produce oxygen and turn barren worlds into living places. Yet, the hardest question remains: how will people themselves make the journey? If faster-than-light travel is never reached, the trip to Andromeda could take hundreds of thousands, or even millions of years. This means that human travelers would have to live not on a planet, but on huge starships called world ships, moving civilizations in themselves. A world ship would carry not only people, but whole ecosystems of plants and animals, recycling systems, factories, and cultural life. Generations of people would be born, live, and die inside the ship, never stepping on Earth or any planet, yet carrying forward the hope of reaching a new galaxy. Other options exist. If humans master the science of deep hibernation, colonists might sleep in dreamless rest for centuries, only to wake upon arrival in Andromeda. Or maybe minds could be copied and turned into digital form, travelling as streams of information within vast artificial intelligence systems. Upon arrival, these minds could be reborn, either in robot bodies or engineered human clones, stepping onto alien soil as if waking from a long dream. When humans finally reach Andromeda, the real challenge of settling would begin. The first bases might not be on planets at all, but in orbit, large space stations near worlds full of resources. These would act as control centres, overseeing exploration and building the foundation for planetary colonies. Over time, networks of such outposts could connect across Andromeda, like stepping stones in a new frontier. Meanwhile, terraforming would continue, slowly shaping alien worlds into places where future generations could breathe without machines. One of the hardest jobs would be building ecosystems from nothing. On Earth, nature had billions of years to grow forests, oceans, and breathable skies. In Andromeda, humans would have to make such environments in just centuries. Artificial biospheres, carefully balanced with engineered food crops and synthetic life, could support early settlers. These colonies would have to be self-sufficient, as they would be cut off from Earth for thousands of years, maybe forever. Without constant contact, these distant human societies would grow on their own, developing cultures, technologies, and governments that might look nothing like those left behind on Earth. The Andromeda plan would also have to prepare for the unknown. If intelligent civilizations already exist in Andromeda, humans would face the delicate issue of first contact. Such an encounter could lead to cooperation, sharing knowledge, and mutual growth, or it could cause conflict on a scale bigger than anything our species has ever known. Rules for diplomacy, careful exploration, and respect for other beings would be essential. Alongside this, defense plans would be needed, not only against possible hostile civilizations, but also against the raw dangers of space itself: asteroids, deadly gamma-ray bursts, supernovas, and even wandering black holes drifting silently between stars. Despite the almost unimaginable challenges, the settling of Andromeda would stand as one of the greatest turning points in human history. It would change us from a species tied to a single galaxy into an intergalactic civilization. To achieve it would be to test every limit of human creativity, courage, and endurance. It would not just expand our place in the universe, it would change what it means to be human. We would carry life across the gap between galaxies, building bridges where there was once only darkness, and showing that imagination and determination can conquer even the greatest cosmic distances. When we look into the night sky, most of the stars we see belong to our own galaxy, the Milky Way. Yet far beyond our familiar starry band lies another huge system, the Andromeda Galaxy, the closest spiral neighbour to our cosmic home. At first sight, the two galaxies look alike. Both are barred spirals with long, sweeping arms. Both are members of the same galactic family called the Local Group, and both are giants compared to their smaller companions. But when astronomers study them more carefully, important differences appear. Differences that show not only how each galaxy has lived its life, but also where they might be going in the future. The Milky Way and Andromeda are not alone in space. Instead, they belong to a galactic neighbourhood known as the Local Group. This collection contains more than 50 galaxies, ranging from giant spirals to tiny, faint dwarfs. Among this group, Andromeda and the Milky Way are by far the largest and most important. They control the gravitational landscape, shaping the paths and futures of smaller galaxies that move around them. One might imagine them as two great kings ruling over a court of lesser companions, each pulling at the others with invisible strings of gravity. Within this group, size and weight matter. The gravitational power of these giants decides which smaller galaxies stay with the group and how interactions happen. Understanding the differences between Andromeda and the Milky Way is therefore not just a matter of curiosity. It helps astronomers trace the story of galaxy growth over billions of years. One of the clearest differences between the two spirals is in their visible size. Andromeda stretches across a huge span of space, measuring about 220,000 light-years from edge to edge. By comparison, the Milky Way is smaller, with estimates ranging from 100,000 to 160,000 light-years across. Even at the smaller end of that range, Andromeda looks like the larger system, its bright arms reaching farther into the cosmic dark. This larger disk suggests a more active past. Galaxies grow not only by forming stars inside themselves, but also by swallowing smaller galaxies that come too close. Andromeda's wide disk may be proof of many such meals, each adding new stars, gas and dust to its structure. The Milky Way has grown too, but its smaller size suggests it may have taken in fewer large companions. While Andromeda looks bigger, bigger does not always mean heavier. Astronomers think that the Milky Way might actually be heavier than its neighbour when the hidden mass of dark matter is included. Dark matter, the strange invisible stuff that weighs more than normal matter by more than 5 to 1, forms halos around galaxies, stretching far beyond the stars we can see. The Milky Way's dark matter halo seems to be especially big and dense, possibly making our galaxy heavier despite its smaller visible disk. This puzzle raises an important question. How do galaxies gain their weight? Does visible size matter more than hidden dark matter? Or do interactions and collisions play the biggest role? Andromeda's wide arms and the Milky Way's heavy halo are different answers to the same cosmic question. When it comes to the number of stars, Andromeda again takes the lead. Astronomers estimate that it holds around 1 trillion stars. That is 1,000 billion shining suns spread across its wide spiral arms and central bulge. The Milky Way, in comparison, has somewhere between 200 and 400 billion stars, a huge number, but still less than half of Andromeda's total. Why the difference? Part of the answer lies in Andromeda's history of star formation and galaxy mergers. By taking in other galaxies and efficiently turning gas into stars, it has built a more crowded city of suns. The Milky Way, though smaller in number, still keeps a healthy star-forming environment, with glowing blue clusters and bright nebulae along its arms. The current speed of star formation tells an even more interesting story. Despite its huge size and population, Andromeda has slowed down a lot in making new stars. Much of its gas has been used up or blown away in past activity, leaving less material for new stars. In contrast, the Milky Way is still fairly active. Large clouds of gas and dust in our spiral arms continue to collapse under gravity, giving birth to new suns that light up regions like the Orion Nebula. This means that while Andromeda shines with the combined light of past star-making, The Milky Way is still younger in spirit, still forming stars at a lively pace. In simple terms, Andromeda looks like an older city where most of the building is done, while the Milky Way is like a busy town still making new neighbourhoods. At the centre of both galaxies lies a dense bulge of stars. Andromeda's bulge is especially big and bright, filled with older, redder stars. Its size suggests that Andromeda has gone through more violent events in its past. When galaxies collide or merge, huge amounts of gas can be driven into the centre, triggering strong bursts of star formation. Over time, these stars grow old, redden, and gather into a dense core. Andromeda's bulge is a record of such dramatic encounters. The Milky Way's central bulge, though still dense and bright, is smaller. This may mean that our galaxy has avoided big collisions for much of its history, or that its interactions were gentler, sending less material into the centre. The difference shows contrasting life stories. Andromeda as the more violent and active sibling, the Milky Way as quieter and calmer. Both galaxies have huge black holes at their centres, objects so massive that not even light can escape their pull. Andromeda's central black hole, often called M31, weighs around 140 million times the mass of the Sun. By comparison, the Milky Way's central black hole, Sagittarius AEM, is much smaller, at about 4 million solar masses. The huge difference suggests that Andromeda's centre has grown more dramatically. It may have swallowed many smaller black holes brought in by merging galaxies, or it may have collected vast amounts of gas over billions of years. Whatever happened, the result is a much larger gravity centre that affects the motions of nearby stars and creates a more energetic core. Galaxies do not stay still, they spin. Stars in their disks orbit the centre at amazing speeds, creating the spiral patterns we see from far away. In Andromeda, stars move around at an average speed of about 250 km per second. In the Milky Way, the average speed is closer to 220 km per second. Though the difference may seem small, it reflects Andromeda's bigger mass and denser bulge. These movements are part of the cosmic dance that holds galaxies together. Without the invisible hand of dark matter, the outer stars would fly away into space. The fact that they stay bound is further proof that a huge halo of unseen mass surrounds each galaxy. Despite their differences, both galaxies share the same basic structure, a barred spiral shape. Their central bulges are crossed by long bars of stars, which act as channels sending gas inward toward the centre. This process fuels star formation and feeds the central black hole, keeping the core active. Such bars are common among spiral galaxies and are thought to come from gravitational changes over time. Beyond the bar, sweeping spiral arms stretch outward, dotted with star-forming regions, clusters and nebulae. These arms are the visible skeleton of the galaxy, showing the places where gas is compressed into new stars. In photos, the similarity between the Milky Way and Andromeda is striking, two majestic pinwheels shining in the dark. Neither galaxy is alone. Each is surrounded by a group of smaller companions, from dwarf galaxies to globular clusters. The Milky Way's best-known satellites are the Large and Small Magellanic Clouds, irregular galaxies visible in the southern sky, along with the Sagittarius Dwarf Galaxy, which is currently being pulled apart by our galaxy's gravity. These companions provide fresh material and occasional collisions that shape the Milky Way's future. Andromeda, too, has its group. Its satellites include M32 and M110, both showing signs of past interactions with their parent galaxy. Interestingly, recent studies suggest that Andromeda's satellites are not randomly scattered, but lie in a surprisingly ordered plane, like they're arranged in a cosmic disk. The Milky Way's satellites, by contrast, appear more randomly spread. This small difference hints at different histories of growth and interaction. Perhaps the most dramatic fact about Andromeda and the Milky Way is that they are moving toward a collision. Gravity is slowly pulling them together, and in about 4 billion years they are expected to meet. At that time, the two giants will merge in a huge cosmic event. Stars will be thrown into new paths, gas will spark in bursts of star formation, and the central black holes may eventually join into a single, even bigger monster. For now, though, both galaxies continue their separate journeys, each telling a different story of growth, struggle, and survival. By comparing their structure, astronomers learn not only about these two neighbours, but also about the big processes that shape galaxies across the universe.